Gravity moves silently, invisibly. But what if it moves not just fast, but ahead of time? What if it knows where objects will be before they get there? Could gravity be predictive? Think about it for a moment. When you drop a ball, gravity doesn't wait to see where the ball is going. It seems to already know. It pulls the ball down in a perfect arc, as if the path was predetermined. When planets orbit the sun, they don't stumble around trying to find their way. They follow precise elliptical paths, as if gravity has already mapped out their entire journey through space. This isn't just poetic thinking. There's real physics behind this mystery. In our everyday experience, information travels at the speed of light. When you see a star in the night sky, you're actually seeing where that star was years ago, because light takes time to reach your eyes. But gravity seems different. It seems to act on where things are right now, not where they were when their light started traveling toward us. Consider two massive objects orbiting each other, like binary stars dancing through space. If gravity worked like light, pulling toward where each star used to be, rather than where it is now, their orbits would spiral outward and the system would quickly fall apart. But that's not what we observe. These cosmic dancers maintain their intricate choreography for millions of years, as if gravity somehow knows exactly where each partner is at every moment. This raises a profound question that cuts to the heart of physics itself. Does gravity operate outside the normal rules of cause and effect? Does it somehow transcend the speed of light barrier that governs every other force in nature? Or is there something deeper going on? Something that reveals the true nature of time itself? Throughout history, humanity has wrestled with the nature of time. Is the future already written, waiting for us to catch up? Or does it emerge moment by moment from the choices and interactions of the present? Gravity might hold the key to these ancient questions. If gravity truly knows the future, it would revolutionize our understanding of reality itself. But before we can explore whether gravity sees the future, we need to grapple with a more fundamental question. In a universe where time itself is relative, where simultaneity breaks down, and where past, present, and future become matters of perspective, what does it even mean to talk about now? What does the present moment look like when viewed through the lens of Einstein's revolutionary insights about space and time? The journey we're about to take will challenge everything you think you know about gravity, time, and the nature of reality itself. We'll discover that gravity isn't quite what it seems, that time isn't what we assumed, and that the relationship between them is far stranger and more beautiful than we ever imagined. This documentary explores what gravity knows and when it knows it. Before we can ask whether gravity sees the future, we need to understand what we mean by the present in the first place. What time is it right now? It seems like the simplest question in the world. You glance at your watch, and there's your answer. But according to the deepest insights of modern physics, that question doesn't actually have a single, universal answer. The concept of now, of a shared present moment that exists everywhere in the universe simultaneously, is one of the most persistent illusions of human experience. To understand why gravity might seem to know the future, we first need to shatter our everyday assumptions about time itself. And the person who first cracked open this mystery was a young patent clerk in Switzerland named Albert Einstein. In 1905, Einstein published his special theory of relativity, and with it, he destroyed the idea of absolute time. But the journey to this revolutionary insight began much earlier, with a puzzle that had been troubling physicists for decades. Light, they had discovered, always travels at the same speed regardless of how fast you're moving when you measure it. This was completely unlike anything else in physics. Consider a simple analogy. If you're driving down a highway at 60 miles per hour and you throw a baseball forward at 30 miles per hour, someone standing by the roadside would measure the baseball's speed as 90 miles per hour. The speeds add up in the way our intuition expects. But light doesn't behave this way. Whether you're standing still, racing toward a light source, or speeding away from it, you always measure light traveling at exactly the same speed, approximately 300 million meters per second. This seemingly impossible result led Einstein to a startling conclusion. Time itself must be flexible. When you move at high speeds, time literally slows down for you relative to stationary observers. This isn't just a measurement error or an illusion, it's a fundamental feature of reality itself. Imagine two observers, Alice and Bob, moving relative to each other at high speed. Alice is on a spaceship traveling at 90% the speed of light, while Bob remains on Earth. Now suppose two events happen in the universe, a supernova explosion in the Andromeda Galaxy and the birth of a star in the Magellanic Clouds. From Bob's perspective on Earth, these two events might appear to happen simultaneously. His clocks, scattered across the universe, all synchronized to Earth time, would register the same moment for both cosmic events. He would say that at exactly 3:15 p.m. Eastern Standard Time, both the supernova exploded and the new star ignited. But Alice, racing through space at tremendous velocity, would see something completely different. Her synchronized clocks would show that one event happened before the other. The supernova might occur first in her reference frame, followed hours or even days later by the stellar birth. Her measurement would be just as valid as Bob's. Who is right? The answer is both of them, and neither of them. There is no absolute simultaneity, no universal now that exists independent of motion. What counts as the present moment depends entirely on how fast you're moving and in which direction. The universe doesn't have a single timeline, it has countless timelines, one for each possible state of motion. This revelation completely upends our everyday experience of time. We're used to thinking of time as a river that flows at the same rate for everyone, carrying all of us downstream at the same pace. But Einstein showed us that time is more like a vast ocean where different currents flow at different rates. Your speed through space determines which current you're caught in. This isn't just a theoretical curiosity. It has been measured and confirmed countless times with exquisite precision. When particles are accelerated to high speeds in laboratories, their internal clocks literally run slower compared to clocks at rest. Muons, unstable particles that normally decay in microseconds, can survive much longer when accelerated to near light speed, because time dilation extends their lifespan from their own perspective. Time dilation isn't science fiction, it's engineering reality. The Global Positioning System satellites orbiting Earth must account for relativistic time effects, or your navigation would be off by miles. These satellites are moving at about 14,000 kilometers per hour relative to Earth's surface, fast enough that their onboard clocks run about 7 microseconds per day, slower than identical clocks on the ground. Without correcting for this effect, GPS accuracy would degrade by about 6 miles per day. But special relativity was just the beginning. Einstein's general theory of relativity, published in 1915, revealed an even more startling truth. Not only does motion affect the flow of time, but so does gravity itself. The stronger the gravitational field, the slower time moves relative to regions of weaker gravity. This gravitational time dilation occurs because gravity and acceleration are equivalent. If you're in a windowless elevator accelerating upward, you cannot tell the difference between that acceleration and being in a gravitational field. This principle, called the equivalence principle, led Einstein to realize that gravity must affect time just as acceleration does. The effects are subtle but measurable everywhere. Time runs slightly faster on the top floor of a skyscraper compared to the ground floor. The difference is incredibly tiny, about 10 nanoseconds per day for a 100-story building, but it's real and detectable. Atomic clocks can measure this gravitational time dilation even over height differences of just a few feet. An astronaut on the International Space Station ages microseconds faster than people on Earth's surface, because they're in a slightly weaker gravitational field. Meanwhile, someone living at sea level ages slightly slower than someone living in the mountains because they're deeper in Earth's gravitational well. These effects accumulate over a lifetime, though the differences remain incredibly small by human standards. But the implications are profound. If time runs at different rates in different gravitational fields, then simultaneity becomes even more complex than special relativity suggested. Two events that appear simultaneous to someone on Earth's surface might not appear simultaneous to someone in orbit or someone on the moon. These discoveries led physicists to a radical new picture of reality called the block universe, or eternalism. In this view, space and time are woven together into a four-dimensional fabric called space-time. Past, present, and future don't unfold in sequence like frames in a movie. They coexist as different regions of this four-dimensional block. Think of it like a loaf of bread. Each slice represents a moment in time, but the entire loaf exists all at once. What we experience as the flow of time is really just our consciousness moving through the block, like a spotlight illuminating different frames of a vast cosmic movie reel. The past hasn't ceased to exist, and the future hasn't yet come into being. They're all equally real, just located in different parts of the space-time block. From this perspective, asking what's happening now in the Andromeda Galaxy is like asking what's happening here when you're standing in New York. The question doesn't make sense without specifying a reference frame, a particular way of slicing through the four-dimensional block to define simultaneity. Different observers moving at different speeds or in different gravitational fields will slice the block differently, creating different definitions of what events are simultaneous. This leads to mind-bending consequences. In principle, there are reference frames in which events we consider to be in our future have already happened, and events we consider to be in our past have not yet occurred. The entire history of the universe, from the Big Bang to the heat death of the cosmos, exists simultaneously in the eternal now of the block universe. But if there's no universal now, if simultaneity is relative and time can flow at different rates, how can anything be the cause of anything else? How do we maintain the logical order of cause and effect that seems so fundamental to how the world works? How do we prevent paradoxes where effects precede their causes? Einstein's answer was the light cone. Every event in space-time is surrounded by a double cone-shaped region that defines what can influence it and what it can influence in return. The past light cone contains all the events that could have causally influenced the present event. The future light cone contains all the events that the present event could causally influence. The boundary of this cone is set by the speed of light in vacuum, approximately 299,792,458 meters per second. Nothing can travel faster than this speed. So no signal, no influence, no information can travel outside the light cone. This creates an absolute limit on causation that remains the same for all observers, regardless of their motion or gravitational environment. Causes must precede their effects within every observer's reference frame, and the maximum speed at which causation can propagate is the speed of light. This speed limit isn't just about electromagnetic radiation, it's about causality itself. It's the maximum rate at which the future can be influenced by the present, the cosmic speed limit that prevents effect from preceding cause. Any violation of this limit would allow paradoxes, situations where effects could travel backward in time to prevent their own causes. Imagine if you could send a signal faster than light to a distant location. Due to the relativity of simultaneity, there would always be some reference frame in which that signal arrived before it was sent. From that frame, information would be traveling backward in time, potentially creating grandfather paradox type situations where effects could interfere with their own causes. The light cone structure preserves causality, while allowing for the relativity of simultaneity. Events outside each other's light cones are space-like separated, meaning they cannot causally influence each other. The order of such events is observer-dependent, but since they cannot affect each other, this doesn't create paradoxes. Only events that are time-like separated, connected by slower-than-light signals, have a definite causal order that all observers agree upon. So in Einstein's universe, simultaneity is relative. Time can run fast or slow depending on motion and gravity. Causation is limited by the speed of light, and past, present, and future coexist in the block of space-time. This creates a very specific structure to how events can influence each other. The past can affect the present through time-like connections. The present can affect the future through the same mechanism, but nothing can reach across space instantaneously to influence events in the present moment of a distant location. This brings us to a profound puzzle that has puzzled physicists for over a century. In this relativistic universe, where simultaneity breaks down and causation is limited by light speed, how can gravity seem to act instantaneously across vast distances? How can Earth's gravity pull on the moon as if it knows exactly where the moon is right now, rather than where it was 1 1/3 seconds ago when light left its surface? If gravity were like other forces transmitting information at the speed of light, then planets would be pulled toward where the sun used to be, not where it is now. Over astronomical timescales, this delay would cause orbits to spiral outward and planetary systems would quickly become unstable. But that's not what we observe. The solar system has remained stable for billions of years, suggesting that gravity somehow acts on present positions rather than past ones. The answer to this puzzle requires us to completely reimagine what gravity actually is. We need to abandon the Newtonian picture of gravity as a force that pulls objects toward each other across empty space, and embrace Einstein's revolutionary insight that gravity is geometry. We need to stop thinking of gravity as something that acts through space, and start thinking of it as the shape of space itself. But gravity doesn't send signals the way light does. It curves the very stage everything moves on. For over 2 centuries, Isaac Newton's vision of gravity dominated human understanding of the cosmos. In his Principia, published in 1687, Newton described gravity as a mysterious force that reaches across empty space to pull massive objects toward each other. The sun pulls on Earth, Earth pulls on the moon, and every particle of matter in the universe tugs on every other particle with a force that depends on their masses and the square of the distance between them. This picture was incredibly successful. It explained the orbits of planets, the motion of comets, the rhythm of tides, and the fall of apples with mathematical precision. But it contained a troubling mystery that Newton himself recognized. How could objects influence each other across the vast emptiness of space without anything connecting them? Newton famously wrote that he would frame no hypotheses about this action at a distance. But the puzzle remained unsolved for centuries. Einstein's genius was to realize that the mystery disappeared entirely if we stopped thinking of gravity as a force pulling through space, and instead thought of it as the curvature of space itself. In general relativity, massive objects don't pull on each other. They warp the fabric of space-time, and other objects simply follow the straightest possible paths through that warped geometry. Imagine space-time as a vast rubber sheet stretched tight. When you place a heavy bowling ball in the center, it creates a depression, a curved region where the formerly flat sheet now has hills and valleys. If you roll a marble across this curved surface, it won't travel in a straight line. Instead, it will curve around the depression, appearing to be attracted to the bowling ball. But there's no force pulling the marble. It's simply following the straightest path available in the curved geometry. This is exactly how Einstein envisioned gravity. massive objects like stars and planets create curvature in the four-dimensional fabric of space-time. Other objects, from asteroids to light rays, follow geodesics through this curved geometry. A geodesic is the generalization of a straight line to curved spaces, the path that represents the shortest distance between 2 points when space itself is warped. When Earth orbits the Sun, it's not being pulled by a gravitational force. Instead, Earth is traveling in a straight line through space-time, but that straight line appears curved to us because space-time itself is curved by the Sun's mass. From Earth's perspective, it's moving inertially, experiencing no forces at all, just as Newton's first law would predict for an object in uniform motion. This might seem like a subtle distinction, but it resolves the mystery of action at a distance completely. There's no force reaching across space because there's no force at all. Objects simply move along the paths that the geometry of space-time makes natural for them to follow. The curvature is local, present everywhere in space-time, not something that has to be transmitted from one location to another. To understand this better, consider the difference between Newtonian and Einsteinian descriptions of a simple scenario. Imagine an astronaut floating in a spacecraft far from any massive objects. In the Newtonian view, the astronaut experiences zero gravitational force and therefore floats weightlessly. Now suppose the spacecraft accelerates upward at 9.8 meters per second squared. The astronaut will be pressed against the floor with exactly the same sensation as standing on Earth's surface. Newton would say this happens because the spacecraft is accelerating upward, while the astronaut, experiencing no forces, continues moving in a straight line. The floor of the spacecraft catches up to the astronaut and pushes against them. Einstein realized something profound. The astronaut cannot tell the difference between being accelerated in empty space and sitting motionless in a gravitational field. This equivalence principle became the foundation of general relativity. If acceleration and gravity are equivalent, then someone in free fall is actually moving inertially, following a straight line through space-time. The person standing on the ground is the one being accelerated, pushed upward by the surface of the Earth against their natural tendency to follow a straight path through the curved space-time created by Earth's mass. This explains why astronauts in orbit around Earth experience weightlessness. They're not escaping Earth's gravity, they're following geodesics through the curved space-time around Earth. From their perspective, they're moving in straight lines, but those straight lines happen to be closed curves that loop around the planet. The sensation of falling that we experience when we jump off a diving board is actually the sensation of moving inertially, following the natural geometry of space-time. The mathematics of general relativity are encoded in Einstein's field equations, published in 1915. These equations relate the curvature of space-time on one side to the energy and momentum of matter on the other. They tell us exactly how mass and energy warp the geometry of space-time, and how that geometry determines the motion of everything within it. The field equations are extraordinarily elegant, but they're also fiendishly difficult to solve in most practical situations. Finding exact solutions requires advanced mathematical techniques and often leads to surprising insights about the nature of space and time. The first exact solution, found by Karl Schwarzschild just months after Einstein published the theory, describes the curved space-time around a spherically symmetric massive object like a star or black hole. But even without solving the equations exactly, we can understand their basic message. Matter tells space-time how to curve, and curved space-time tells matter how to move. This creates a dynamic, evolving geometry where the distribution of mass and energy at each moment determines the shape of space-time, which in turn determines how objects will move in the next moment. This is radically different from Newton's picture of gravity as a force transmitted through absolute space and time. In Einstein's view, there is no absolute space or time, only the dynamic geometry of space-time that changes in response to the matter and energy it contains. Gravity isn't something that acts in space-time, it is the curvature of space-time itself. One of the most striking predictions of this geometric view is gravitational time dilation, which we touched on in the previous chapter. In regions of strong gravitational field, where space-time is highly curved, time runs slower relative to regions of weaker field. This isn't just an effect on clocks, it's a fundamental feature of the geometry itself. Time and space are so intimately connected that warping one necessarily affects the other. Another prediction is the bending of light by gravity. In Newton's theory, light, having no mass, should be unaffected by gravitational forces. But in Einstein's theory, light follows geodesics through curved space-time, just like everything else. When light passes near a massive object, its path curves, creating gravitational lensing effects that we can observe astronomically. The first test of this prediction came during a solar eclipse in 1919, when Arthur Eddington measured the apparent positions of stars near the sun's edge. The starlight was bent by exactly the amount Einstein's theory predicted, providing dramatic confirmation that gravity really is the curvature of space-time. Perhaps most remarkably, the geometric view of gravity makes testable predictions about phenomena that don't exist in Newton's theory at all. When massive objects accelerate, they create ripples in the fabric of space-time itself. These gravitational waves propagate outward at the speed of light, carrying energy away from their sources and gradually changing the curvature of space-time as they pass. Einstein initially thought these waves would be too weak to detect, but advances in technology have made direct detection possible. In September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves from two merging black holes over 1 billion light-years away. The signal lasted only a fraction of a second, but it provided direct evidence that space-time really does behave like a dynamic, flexible fabric that can vibrate and carry waves. These discoveries confirm Einstein's geometric picture of gravity in the most direct way possible. We're not just inferring the curvature of space-time from the motion of objects within it. We're detecting the vibrations of space-time itself as gravitational waves wash over our detectors. The fabric of reality literally stretches and contracts as these waves pass, changing the measured distance between test masses by amounts smaller than 1/10,000th the width of a proton. But this geometric understanding of gravity creates new puzzles about the nature of time and causation. If gravity is just geometry, if objects are simply following predetermined paths through a curved space-time, what role does time play in the unfolding of gravitational interactions? How do changes in the distribution of matter propagate through the geometric structure of space-time? In Newton's theory, if the sun suddenly disappeared, Earth would immediately feel the change and fly off in a straight line. The gravitational force would instantly adjust to reflect the new configuration of masses. But in Einstein's theory, changes in the gravitational field propagate at the speed of light. If the sun vanished, Earth would continue orbiting for about 8 minutes, until the gravitational waves carrying news of the sun's disappearance finally reached our planet. This seems to solve the problem of instantaneous action at a distance. Gravitational influences are limited by the speed of light, just like all other causal influences in relativity. But it creates a new puzzle. If gravitational changes propagate at light speed, why don't planetary orbits decay over time due to the delay between where objects are and where their gravitational influence points? The answer lies in the sophisticated mathematical structure of Einstein's field equations. Unlike Newton's inverse square law, which depends only on the instantaneous positions of masses, Einstein's equations incorporate the effects of motion, momentum, and energy flow in ways that naturally account for the finite speed of gravitational influences. When we solve Einstein's equations for slowly moving objects like planets, we find that the effects of retardation, the delay in gravitational influences, are almost exactly cancelled by additional terms that depend on the velocities and accelerations of the masses involved. The result is orbital motion that appears to respond to instantaneous positions, even though all the underlying influences respect the speed of light limit. This is one of the most elegant features of general relativity. The equations automatically build in the right combination of retarded effects and velocity-dependent terms to preserve the stability of bound systems like planetary orbits and binary stars. There's no need for gravity to violate causality or act faster than light. The geometric structure of space-time, evolving according to Einstein's field equations, naturally produces the appearance of instantaneous gravitational action while respecting the fundamental speed limit of relativity. Yet questions remain about how this geometric picture relates to our earlier discussion of time and simultaneity. If space-time is a four-dimensional block where past, present, and future coexist, how do we understand the apparently dynamic evolution of gravitational fields? How does the curvature of space-time encode information about the future motion of the objects within it? These questions become even more intriguing when we consider orbital motion in detail. Planets don't just respond to where other objects are now, they seem to anticipate where those objects are going. The intricate dance of multiple body systems like the moons of Jupiter or the complex choreography of binary star systems suggests a level of coordination that goes beyond simple response to current conditions. But what shapes that path and when? Every 88 days, Mercury completes another journey around the Sun, tracing an elliptical path with clockwork precision. Venus follows suit every 225 days, Earth every 365¼ days, and the outer planets maintain their own stately rhythms over periods measured in years or decades. This cosmic choreography has continued for billions of years with almost perfect regularity, a testament to the stability and predictability of gravitational interactions. But this stability hides a profound mystery that goes to the heart of how gravity operates in Einstein's relativistic universe. If gravity works like other forces, transmitting influences at the finite speed of light, then planets should be responding to where the Sun was minutes ago, not where it is now. Over cosmic timescales, this delay should cause orbits to spiral outward, and the solar system should have fallen apart long ago. Consider the Earth-Sun system in detail. Light takes approximately 8 minutes and 20 seconds to travel from the Sun's surface to Earth. If gravity worked like a simple signal propagating at light speed, Earth's orbital motion would be responding to where the Sun was 8 minutes ago. But during those 8 minutes, the Sun has moved slightly in its own orbit around the galactic center, and Earth has traveled thousands of kilometers along its orbital path. In Newton's theory, this wasn't a problem because gravitational forces were assumed to act instantaneously across any distance. The moment the Sun moved, Earth would immediately feel the change and adjust its motion accordingly. But Einstein's relativity forbids faster than light influences. Everything, including gravity, must respect the cosmic speed limit. This creates what physicists call the retardation problem. If we naively apply the finite speed of light to gravitational interactions, we get orbital mechanics that don't match what we observe in nature. Planets pulled toward the retarded positions of their parent stars would experience a drag force that slowly increases their orbital periods. Binary star systems should spiral outward and eventually unbind. The universe should be littered with the remnants of disrupted planetary systems. Yet when we look at the cosmos, we see exactly the opposite. Planetary systems like our own remain stable for billions of years. Binary stars maintain tight orbits over astronomical time spans. The dance of Jupiter's moons continues with metronomic precision century after century. Something about gravity allows it to maintain stable orbital relationships despite the finite speed of light. The resolution of this puzzle reveals one of the most elegant aspects of Einstein's general relativity. The theory doesn't just account for the finite speed of gravitational influences. It automatically incorporates additional effects that nearly perfectly cancel the destabilizing retardation forces. To understand how this works, we need to dive deeper into the mathematical structure of Einstein's field equations. Unlike Newton's simple inverse square law, which depends only on the masses and positions of objects, Einstein's equations include terms that depend on velocities, accelerations, and the flow of energy and momentum through space-time. When we solve these equations for the case of two objects in orbit around each other, we find something remarkable. Yes, there are retarded gravitational effects that point toward where objects used to be rather than where they are now. But there are also additional velocity-dependent terms, sometimes called gravitomagnetic effects, that nearly perfectly compensate for the retardation. Think of it this way. The curvature of space-time doesn't just depend on where masses are located, it also depends on how they're moving. A moving mass creates not just a static gravitational field, but also a kind of gravitational analog to magnetism. Just as a moving electric charge creates both electric and magnetic fields, a moving mass creates both gravitational and gravitomagnetic fields. These gravitomagnetic effects are incredibly subtle, but they're precisely calibrated to cancel the orbital decay that retardation would otherwise cause. When we work out the mathematics for slowly moving objects like planets, the retarded gravitational attraction pointing toward the past position of the Sun is almost exactly balanced by gravitomagnetic forces that effectively point toward the future position. The result is orbital motion that appears to respond to instantaneous positions, even though every component of the interaction respects the speed of light. It's as if gravity has built-in error correction that compensates for the time delays inherent in any finite speed interaction. This cancellation isn't approximate, it's exact to an extraordinary degree of precision for most astronomical systems. The residual orbital decay, what physicists call gravitational wave radiation damping, is typically so small that it would take longer than the age of the universe to significantly affect planetary orbits. But this error correction isn't perfect in all circumstances. For systems where objects move at significant fractions of the speed of light, or where gravitational fields are extremely strong, the cancellation becomes incomplete. This leads to a gradual loss of orbital energy through the emission of gravitational waves, causing orbits to slowly decay over time. The first indirect detection of gravitational waves came from observations of just such a system. In 1974, Russell Hulse and Joseph Taylor discovered a pulsar, a rapidly rotating neutron star, locked in a tight orbit with another neutron star. This system, known as the Hulse-Taylor pulsar, or PSRB 1913+16, provided the perfect laboratory for testing Einstein's predictions about gravitational wave emission. Because one of the neutron stars is a pulsar, it acts like a cosmic lighthouse, sweeping a beam of radio waves across Earth with incredible regularity. By timing the arrival of these pulses with extraordinary precision, astronomers could track the orbital motion of the system down to fractions of a second. What they found was a gradual decrease in the orbital period, exactly matching Einstein's prediction for energy loss through gravitational wave radiation. The orbit was decaying at a rate of about 76 microseconds per year, causing the two neutron stars to spiral slowly inward toward an eventual collision billions of years in the future. This observation provided the first indirect evidence that gravitational waves really exist, confirming one of the most subtle predictions of general relativity. It also demonstrated that the error correction mechanism that keeps most orbits stable does indeed break down under extreme conditions. leading to measurable orbital evolution. The discovery earned Hulse and Taylor the Nobel Prize in Physics in 1993, 20 years before the first direct detection of gravitational waves by LIGO. Their work showed that gravity's apparent ability to act instantaneously is really the result of a delicate balance between retarded effects and compensating forces, a balance that breaks down only in the most extreme environments. But even this understanding raises deeper questions about the nature of gravitational interactions. How does the mathematical machinery of general relativity know to include exactly the right velocity-dependent terms to maintain orbital stability? Why does the curvature of space-time naturally encode both the retarded effects of finite light speed and the compensating gravitomagnetic forces? The answer lies in the deep geometric structure of Einstein's theory. General relativity isn't just a theory about gravitational forces, it's a theory about the fundamental nature of space-time itself. The field equations don't just describe how masses pull on each other, they describe how the presence of matter and energy determines the very geometry within which all motion takes place. This geometric view automatically ensures that the laws of physics remain consistent across all reference frames. The same mathematical structure that guarantees energy and momentum conservation also ensures that orbital mechanics work correctly, despite the finite speed of light. The theory is, in a sense, self-correcting. Consider what happens when we view orbital motion from the perspective of one of the orbiting objects. From Earth's reference frame, it's not moving at all. It's simply sitting at rest in the curved space-time created by the sun's mass. The curvature of this space-time naturally defines geodesic paths that loop back on themselves, creating stable orbital motion without any need for action at a distance or faster than light communication. The sun's motion through the galaxy, which might seem to complicate the gravitational calculation, is automatically accounted for by the geometric structure of space-time itself. The curvature adjusts continuously to reflect the true distribution of mass and energy, including all motion and momentum at each point in space-time. This provides a completely local description of gravitational interactions. There's no need for Earth to know where the sun is at any given moment, because Earth is simply following the natural geometry of the space-time it finds itself in. That geometry is shaped by all the matter and energy in the vicinity, taking into account their positions, velocities, and accelerations in a completely self-consistent way. Yet this local geometric picture seems to conflict with our earlier discussion of retardation and gravitational wave propagation. If changes in gravitational fields propagate at the speed of light, how can the local geometry always perfectly reflect the current state of distant masses? The resolution involves understanding that gravitational waves carry information about accelerations, not positions or velocities. When massive objects accelerate, they create ripples in space-time that propagate outward at light speed. But the background curvature created by slowly moving masses evolves much more smoothly, without generating significant wave radiation. For typical astronomical systems like planetary orbits, the relevant timescales for orbital motion are much longer than the light travel time across the system. Earth takes a year to orbit the Sun, but light crosses the solar system in hours. This separation of timescales allows the quasi-static gravitational field to remain approximately synchronized across the system, even though changes propagate at finite speed. It's analogous to the way a slowly rotating water wheel creates a smooth, predictable flow pattern, even though disturbances in the water propagate at finite speed. The key is that the rotation is slow compared to the wave propagation time across the system. Fast changes create waves that carry away energy, but slow changes simply modify the quasi-static background field. This explains why planetary orbits remain stable over cosmic timescales, while rapidly changing systems like merging black holes emit copious gravitational waves and lose energy quickly. The mathematics of general relativity automatically distinguishes between these regimes, providing the right physics for each situation without any ad hoc assumptions or fine-tuning. But the story becomes even more intriguing when we consider systems with multiple gravitating bodies. The three-body problem, involving three masses interacting gravitationally, has no general analytical solution even in Newton's theory. In Einstein's theory, with its additional complexity from retardation and gravitomagnetic effects, the situation becomes vastly more complicated. Yet nature presents us with many stable multi-body systems. The Galilean moons of Jupiter have maintained their orbital resonances for billions of years. The Saturnian moon system displays an intricate web of gravitational interactions that keep dozens of moons and countless ring particles in stable configurations. These systems seem to possess an almost uncanny ability to maintain long-term stability despite their complexity. Recent computer simulations of these systems using the full machinery of general relativity show that the error correction mechanism we discussed for two-body orbits extends naturally to multi-body systems. The retardation effects and gravitomagnetic compensations work together to maintain stability even in complex gravitational environments. But these simulations also reveal something unexpected. In some configurations, the interplay between retardation and gravitomagnetic effects can create what appears to be anticipatory behavior. The system seems to adjust its motion in response to future changes in the gravitational field, as if gravity has some knowledge of what's coming next. This apparent prescience isn't really foresight, but it reflects the deep geometric nature of gravitational interactions. The curvature of space-time encodes not just the current positions and velocities of masses, but also their natural evolutionary trajectories. Objects following geodesics through this curved geometry naturally move in ways that anticipate the future evolution of the system. It's as if the shape of space-time itself contains information about the future motion of the objects within it. This raises profound questions about the relationship between geometry and time, between the structure of space-time and the unfolding of physical events. Does gravity anticipate motion, or does motion anticipate gravity? In Einstein's geometric view, this distinction begins to blur, leading us toward even stranger territory, where the very concepts of past, present, and future require careful re-examination. So gravity doesn't see the future, but it can respond to the present in ways that light can't, or can it? When you watch a skilled ballet dancer leap through the air, there's something almost magical about how they seem to know exactly where they'll land before they get there. Their arms position themselves for the landing, their legs prepare for the impact, their entire body moves with a fluid anticipation of future events. But we understand this apparent foresight. The dancer's brain calculates trajectories, muscle memory guides motion, and physics determines the inevitable path through space. Gravity seems to display a similar kind of anticipation, but far more mysterious. When binary stars orbit each other, they don't just respond to where their partner is right now. They seem to know where their partner is going to be, adjusting their motion in ways that maintain stable orbits over cosmic timescales. This apparent prescience has puzzled physicists for decades and led some to wonder whether gravity operates outside the normal rules of cause and effect. To understand this mystery, we need to compare gravity with the other fundamental forces of nature, particularly electromagnetism. The parallels and differences between these forces reveal crucial insights about how information propagates through space and time, and whether any force can truly anticipate the future. Consider two charged particles orbiting each other, bound together by electromagnetic attraction. In many ways, this system resembles a gravitational binary, with electric forces playing the role of gravitational attraction. But there's a crucial difference. When electromagnetic interactions are calculated using the full machinery of Maxwell's equations and special relativity, orbiting charged particles lose energy rapidly through electromagnetic radiation. This energy loss causes the orbit to decay quickly. Two electrons orbiting each other like a miniature solar system would spiral inward and collide in a tiny fraction of a second. The electromagnetic field responds to where the charges were in the past, creating retardation effects that aren't compensated by any analog to the gravitomagnetic corrections we discussed for gravity. This difference between electromagnetic and gravitational interactions provides a crucial clue about gravity's apparent anticipatory behavior. Electromagnetic fields are what physicists call vector fields, described mathematically by quantities that have both magnitude and direction. The electromagnetic field at any point in space points in a specific direction with a specific strength. Gravitational fields, in contrast, are tensor fields, described by mathematical objects that are more complex than simple vectors. Tensors can encode not just the strength and direction of gravitational effects, but also information about how those effects change with motion, acceleration, and the flow of energy through space. This additional mathematical complexity isn't just abstract formalism. It reflects a fundamental difference in how gravity and electromagnetism couple to their source materials. Electric charges create electromagnetic fields that depend primarily on the positions and velocities of the charges. But masses and energy create gravitational fields that depend on positions, velocities, accelerations, momentum flow, stress, and pressure in intricate, interconnected ways. When a massive object moves through space, it doesn't just carry its gravitational field along like a charged particle carries its electric field. Instead, the moving mass continuously reshapes the geometric structure of spacetime itself, creating patterns of curvature that naturally encode information about both past motion and future evolution. This encoding happens through what mathematicians call the geodesic equation, the fundamental equation that describes how objects move in curved spacetime. When we solve this equation for a particle moving in the gravitational field of another object, we find that the particle's future trajectory is completely determined by the current geometry of spacetime in its immediate vicinity. But here's the remarkable part. That local geometry contains information not just about where the other object is now, but about how it's moving and how its motion is changing. The curvature of spacetime acts like a kind of memory storage system, preserving information about the momentum and acceleration of distant masses in the very fabric of space and time. This means that an object following a geodesic through curved spacetime automatically anticipates the future motion of the masses that created that curvature. It's not that gravity sees the future, but rather that the present state of the gravitational field already contains information about how that field will evolve in the immediate future. Think of it like reading the current in a river. An experienced kayaker can look at the water flow around them and predict where they'll be carried in the next few seconds. The current patterns visible now contain information about the future motion of anything moving with the flow. Similarly, the curvature patterns in spacetime contain information about the future motion of objects following geodesics through that curved geometry. This analogy isn't perfect because river currents are created by fixed boundaries like banks and rocks, while gravitational fields are created by the very objects that move through them. It's more like a river, where the water flow is created by floating objects that are themselves carried along by the current they help create. This self-consistent, dynamic relationship is what makes gravitational systems so remarkably stable. The mathematical machinery that makes this work is encoded in Einstein's field equations through what are called the Bianchi identities. These mathematical relationships ensure that energy and momentum are conserved automatically in any solution to the field equations. They guarantee that the curvature of space-time evolves in a way that preserves the total energy and momentum of everything within it. These conservation laws have profound implications for how gravitational interactions unfold over time. They ensure that the energy lost by orbital motion through gravitational wave radiation is exactly balanced by the energy carried away by those waves. They guarantee that momentum changes in one part of a system are compensated by opposite momentum changes elsewhere. Most importantly for our discussion, they ensure that the current state of the gravitational field contains exactly the right information to predict its own future evolution. The field equations are what mathematicians call hyperbolic partial differential equations, meaning that the future state of the field at any point is completely determined by the current state in a neighborhood around that point. This is similar to how the motion of waves on a stretched string is determined by the current shape and velocity of the string. If you know the exact configuration of the string right now, you can predict how the waves will evolve in the future. Similarly, if you know the exact configuration of the gravitational field right now, including all the subtle momentum and energy flows it encodes, you can predict how that field will evolve. But there's a crucial difference between waves on a string and gravitational fields in space-time. The string is a passive medium that carries waves created by external forces. Space-time is an active medium that participates in its own evolution. The curvature of space-time determines how matter moves, but the motion of matter determines how space-time curves. This creates what physicists call a non-linear system, where the solutions can display complex, emergent behaviors that aren't obvious from the underlying equations. In some cases, this non-linearity can create what appears to be anticipatory behavior, where the system seems to adjust its evolution in response to future changes. Consider a specific example that illustrates this apparent anticipation. Imagine a binary system where two neutron stars are spiraling toward each other under the influence of gravitational wave radiation. As they get closer, they move faster, and their gravitational fields become more dynamic. The rate of energy loss through gravitational waves increases, causing the orbital decay to accelerate. But here's what's remarkable. Long before the final merger, the orbital motion of the neutron stars begins to anticipate the strong field effects that will dominate the final moments of the coalescence. The orbit starts to deviate from simple Keplerian motion in ways that can only be understood by considering the full nonlinear evolution of the Einstein field equations. It's as if the system knows that it's heading toward a merger and begins to prepare for that event well in advance. The gravitational field starts to encode information about the final catastrophic collision millions of orbits before it actually happens. This information isn't transmitted from the future, it's generated by the non-linear evolution of the current gravitational configuration. Recent computer simulations of black hole mergers reveal similar anticipatory behavior. The space-time around merging black holes develops complex patterns of curvature that seem to anticipate the final merger, even when the black holes are still separated by many times their own radii. These patterns guide the motion of the black holes along trajectories that lead inevitably to collision and merger. This apparent foresight emerges naturally from the mathematical structure of general relativity, without requiring any violation of causality or faster than light information transfer. The field equations automatically generate solutions where the current state of the system contains information about its own future evolution. But this raises a deeper question about the nature of time and causation in Einstein's universe. If the present gravitational field contains information about future motion, in what sense is that motion truly in the future? Are we dealing with genuine prediction? Or are we seeing evidence that past, present, and future are more intimately connected than our everyday experience suggests? The block universe picture we discussed earlier provides one way to think about this puzzle. In the four-dimensional space-time block, all events past, present, and future coexist simultaneously. What we experience as the unfolding of gravitational interactions over time is really just different cross-sections through this four-dimensional structure. From this perspective, gravitational anticipation isn't mysterious at all. The curvature at any point in the space-time block naturally reflects the distribution of matter and energy throughout the entire four-dimensional structure. An object following a geodesic through this curved geometry automatically moves along a path that appears anticipatory from our three-dimensional, time-based perspective. But even this geometric picture raises questions about the ultimate nature of causation. If the future already exists in the space-time block, what sense does it make to talk about causes and effects? How do we understand the apparent flow of time and the seeming unpredictability of quantum events? These questions become even more intriguing when we consider what happens at the intersection between gravity and quantum mechanics. While general relativity treats space-time as a smooth, continuous manifold, quantum mechanics suggests that at the smaller scales, space and time themselves might be quantized, made up of discrete, indivisible units. Some theoretical physicists have proposed that quantum effects might introduce genuine unpredictability into gravitational interactions, breaking the deterministic evolution described by Einstein's classical field equations. Others suggest that quantum entanglement might create non-local correlations that allow gravitational effects to propagate faster than light under certain circumstances. These ideas remain highly speculative, with no experimental evidence to support them, but they raise fascinating questions about whether gravity's apparent anticipatory behavior might reflect deeper quantum mechanical principles that we don't yet understand. Another speculative possibility involves the holographic principle, an idea emerging from string theory and black hole physics. This principle suggests that all the information contained in a volume of space can be encoded on the boundary of that volume, much like a hologram encodes three-dimensional information on a two-dimensional surface. If the holographic principle applies to gravity, it might explain how gravitational fields can contain information about future evolution. The information about future motion might be encoded holographically in the present structure of space-time, accessible to objects moving through that space without requiring faster than light information transfer. But these remain theoretical speculations, far from experimental verification. What we know for certain is that gravity displays apparent anticipatory behavior that emerges naturally from the mathematical structure of general relativity without requiring any violation of causality or departure from well-established physics. The key insight is that gravity isn't just another force acting through space and time. It is the curvature of space and time themselves. This curvature naturally encodes information about momentum, acceleration, and energy flow in ways that allow objects moving through curved space-time to anticipate the future evolution of the gravitational field. This anticipation isn't perfect or unlimited. It extends only as far as the local curvature of space-time can reliably predict, typically over timescales short compared to the light-crossing time of the system. For longer-term prediction, the finite speed of gravitational wave propagation imposes fundamental limits on how much the gravitational field can know about distant future events. But within these limits, gravity does display a remarkable ability to encode information about future motion in its present structure. This encoding allows gravitational systems to maintain stable configurations over cosmic timescales, creating the intricate astronomical choreography we observe throughout the universe. Still, some theorists argue that gravity feels different, like it's more than just another field. Could there be something deeper going on? Something that connects gravity to the fundamental structure of information and reality itself? At the heart of modern physics lies an uncomfortable truth. Our two most successful theories, quantum mechanics and general relativity, fundamentally disagree about the nature of reality. Quantum mechanics describes a world of uncertainty, probability, and instantaneous correlations that seem to transcend space and time. General relativity describes a world of smooth geometry, deterministic evolution, and strict adherence to the speed of light limit. These theories have never been successfully unified, and their conflict becomes most apparent in extreme environments where both quantum effects and strong gravity are important. This tension is more than just an academic puzzle. It strikes at the heart of our question about gravity's relationship with time and causality. If gravity emerges from quantum mechanical processes, as many physicists suspect, then its apparent ability to anticipate future motion might reflect deeper quantum principles that operate outside our normal understanding of cause and effect. The story begins with one of the most mysterious aspects of quantum mechanics, a phenomenon that Einstein famously called spooky action at a distance. When two particles become quantum mechanically entangled, measuring the properties of one particle instantly affects the other, regardless of how far apart they are. These correlations appear to violate the speed of light limit, creating what seems like instantaneous communication across arbitrary distances. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, argued in 1935 that this apparent non-locality must mean that quantum mechanics is incomplete. They proposed that hidden variables, unknown to us, but determining the behavior of quantum systems, must exist to restore locality and causality to physics. This became known as the Einstein-Podolsky-Rosen paradox, or EPR paradox. For decades, this remained a purely philosophical debate. But in 1964, physicist John Bell proved that no theory based on local hidden variables can reproduce all the predictions of quantum mechanics. Bell's theorem showed that any complete description of nature must either be non-local, allowing instantaneous influences across space, or non-realistic, denying that particles have definite properties independent of measurement. Subsequent experiments, beginning with Alain Aspect's groundbreaking work in the 1980s, have confirmed Bell's predictions with ever-increasing precision. Quantum entanglement really does create correlations that appear to transcend space and time, operating faster than light and connecting distant regions of the universe in ways that classical physics cannot explain. This creates a puzzle for our understanding of gravity. If quantum mechanics is fundamental, and if gravity emerges from quantum processes, then gravitational interactions might inherit some of the non-local properties of quantum entanglement. This could potentially explain gravity's apparent ability to maintain stable orbits despite light speed delays, or even allow for genuine anticipation of future events. Some theoretical physicists have proposed that space-time itself might be constructed from quantum entanglement. In this view, the geometric connections that we experience as the fabric of space and time are really manifestations of quantum correlations between microscopic degrees of freedom that we can't directly observe. This idea, known as the entanglement theory of space-time, suggests that the smooth curvature described by Einstein's field equations emerges from a deeper quantum substrate made up of vast networks of entangled quantum states. The apparent continuity of space and time would be an illusion, like the apparent smoothness of a computer screen that's actually made up of discrete pixels. If this picture is correct, then gravity's relationship with causality might be fundamentally different from what we've assumed. The quantum entanglement underlying space-time could create non-local correlations that allow gravitational effects to coordinate across vast distances without being limited by the speed of light. This might explain how binary star systems maintain their stability, or how galaxies hold together despite the apparent insufficiency of visible matter to provide the necessary gravitational binding. The mathematics of this approach draws heavily from recent developments in string theory and the holographic principle. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in a space with more than our familiar 3 spatial dimensions. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, much like a hologram encodes 3-dimensional information on a 2-dimensional surface. When these ideas are combined, they paint a picture of space-time as an emergent phenomenon arising from quantum information processing on the boundary of space. The interior of any region, including its gravitational field and the motion of objects within it, would be completely determined by quantum information encoded on the boundary. This holographic encoding could potentially allow for what appears to be anticipatory behavior. If the future evolution of a gravitational system is already encoded in boundary information that exists in the present, then objects moving through the interior could appear to anticipate future changes by accessing this holographically stored information. But these ideas remain highly speculative. While string theory and the holographic principle have led to important insights in theoretical physics, they have not yet made testable predictions that can be verified experimentally. The energy scales at which quantum gravitational effects become important are typically far beyond what we can probe with current technology. The Planck scale, where quantum effects and gravitational effects become equally important, corresponds to energies about 10 to the 16th times higher than those accessible in the most powerful particle accelerators. At these energies, the smooth space-time of general relativity is expected to break down into a foam-like structure, where the very concepts of space and time lose their meaning. Some physicists have proposed that this quantum foam might create a kind of cosmic information processing network, where quantum computations performed at the Planck scale determine the large-scale evolution of space-time. In this view, gravity's apparent anticipatory behavior might reflect the outcome of quantum calculations that take into account information from throughout the causal structure of space-time. This quantum computational view of space-time draws inspiration from recent work on quantum information and computation. Quantum computers can perform certain calculations exponentially faster than classical computers by exploiting the superposition and entanglement properties of quantum states. If space-time itself operates as a kind of quantum computer, it might be able to process information about future evolution in ways that classical systems cannot. Recent theoretical work has explored connections between quantum error correction, the process by which quantum computers protect information from decoherence, and the structure of space-time near black holes. Some researchers have proposed that the same mathematical techniques used to design fault-tolerant quantum computers might explain how space-time maintains its geometric structure despite quantum fluctuations. These quantum error-correcting codes might also explain how gravitational systems maintain their stability over cosmic timescales. Just as error correction allows quantum computers to perform reliable calculations despite noise and interference, quantum error correction in space-time might allow gravitational systems to maintain stable configurations despite quantum uncertainty. But perhaps the most intriguing possibility involves the relationship between quantum entanglement and black holes. Black holes represent the most extreme gravitational environments in the universe, where the curvature of space-time becomes so intense that not even light can escape. They also represent the boundary between the classical world of general relativity and the quantum world where new physics must emerge. Stephen Hawking's discovery in 1974 that black holes emit thermal radiation created a paradox that continues to puzzle physicists today. According to quantum mechanics, information cannot be destroyed, but Hawking radiation appears to be completely thermal, carrying no information about what fell into the black hole. If the black hole eventually evaporates completely through Hawking radiation, what happens to the information that fell in? This information paradox has led to proposals that black holes might be connected to the fundamental structure of quantum information in spacetime. Some physicists suggest that black holes store information holographically on their event horizons, where it remains accessible to outside observers even as matter falls inward. Others propose that black holes might be connected through wormholes, creating quantum entanglement between distant regions of spacetime. In this view, the interior of one black hole might be quantum mechanically connected to the interior of another, allowing information to tunnel between them through mechanisms that transcend classical spacetime geometry. These ideas have led to speculation about whether black holes might serve as cosmic information processing centers, performing quantum computations that affect the evolution of spacetime on large scales. If this is true, then gravity's apparent anticipatory behavior might reflect the output of quantum calculations performed by black hole networks throughout the universe. Some researchers have even proposed that our entire universe might be the interior of a black hole, with all the information about our reality encoded holographically on a distant boundary that we can never directly access. In this scenario, what we experience as the evolution of space-time over cosmic time would be the unfolding of a vast quantum computation performed on this holographic boundary. But while these ideas are fascinating, they remain far from experimental verification. The energies and length scales involved in quantum gravity are typically far beyond current observational capabilities. We can observe the effects of strong gravitational fields around black holes and neutron stars, and we can study quantum mechanics in laboratory settings, but we cannot yet probe the regime where both effects become important simultaneously. This leaves us in the intriguing position of having compelling theoretical reasons to suspect that gravity's relationship with time and causality might be more complex than general relativity suggests, while lacking direct experimental evidence for quantum gravitational effects. The apparent anticipatory behavior of gravitational systems might reflect deep quantum mechanical principles, or it might be fully explained by the classical nonlinear dynamics of Einstein's field equations. Recent advances in gravitational wave astronomy have begun to provide new windows into strong field gravity that might eventually reveal quantum gravitational effects. The LIGO and Virgo detectors have observed dozens of black hole and neutron star mergers, providing unprecedented information about how spacetime behaves under extreme conditions. Future gravitational wave detectors, including space-based instruments like the Laser Interferometer Space Antenna, will be sensitive to gravitational waves from supermassive black hole mergers and other exotic sources. These observations might reveal deviations from general relativity that could provide the first direct evidence of quantum gravitational effects. Similarly, advances in quantum information theory and quantum computing might provide new theoretical tools for understanding how quantum mechanics and gravity might be unified. Quantum computers might eventually become powerful enough to simulate quantum gravitational systems directly, providing insights that are impossible to obtain through analytical calculations alone. But even without direct experimental evidence, the theoretical exploration of quantum gravity has already transformed our understanding of space-time, information, and the relationship between them. These investigations suggest that gravity's apparent anticipatory behavior might be just the tip of an iceberg, reflecting deep connections between geometry, quantum mechanics, and information that we're only beginning to understand. The possibility that space-time itself emerges from quantum entanglement, that black holes process quantum information, and that the universe might be performing vast quantum computations at scales we can barely imagine, opens up entirely new ways of thinking about gravity's relationship with time and causality. Could black holes, the most extreme gravitational objects, reveal more about how gravity relates to time? Do these cosmic information processes hold the key to understanding whether gravity truly anticipates the future, or whether our concepts of past, present, and future need to be fundamentally reconsidered? In the center of our galaxy, 4 million times the mass of our Sun is compressed into a region smaller than the orbit of Mercury. This supermassive black hole, known as Sagittarius A star, sits like a cosmic spider at the center of a web of gravitational influence that extends throughout the Milky Way. From our perspective, 26,000 light-years away, it appears almost benign, a dark object detectable only by its gravitational effects on nearby stars. But venture closer, and you encounter one of the most extreme and mysterious objects in the universe. Black holes represent the ultimate test of our understanding of gravity, time, and causality. They are regions where Einstein's equations predict that space-time curvature becomes so extreme that the normal relationship between cause and effect breaks down completely. At the boundary of a black hole, called the event horizon, time itself appears to stop from the perspective of outside observers. Beyond that boundary lies a realm where all paths through space-time lead inexorably toward a central singularity, where the laws of physics as we know them cease to apply. These extreme gravitational environments provide a unique laboratory for exploring our central question about gravity's relationship with time. If gravity has any special ability to transcend normal causality, to anticipate future events, or to operate outside the standard speed of light limitations, black holes are where we might expect to see such effects most clearly. The journey toward understanding black holes began not with Einstein, but with an English clergyman named John Michell. In 1783, Michell calculated that if a star were massive and compact enough, not even light could escape its gravitational pull. He called these hypothetical objects dark stars, and his calculation, based on Newton's theory of gravity, predicted objects remarkably similar to what we now call black holes. But it was Einstein's general relativity that revealed the true strangeness of these objects. Just months after Einstein published his field equations in 1915, Karl Schwarzschild found an exact solution describing the curved spacetime around a spherically symmetric, massive object. Schwarzschild was a German physicist serving on the Russian front during World War I, and he completed this calculation shortly before his death from typhus in 1916. The Schwarzschild solution revealed something unprecedented in physics. At a specific radius, now called the Schwarzschild radius, or event horizon, the mathematics seemed to break down. Time dilation became infinite, space appeared to curve back on itself, and the normal relationship between space and time coordinates became meaningless. For decades, physicists wondered whether these mathematical pathologies represented real physical phenomena or just artifacts of the coordinate system Schwarzschild had chosen. The resolution came through the work of physicists like David Finkelstein, Martin Kruskel, and George Sekeres, who showed that the apparent singularity at the event horizon was indeed a coordinate artifact. Space and time remain perfectly well behaved at the horizon, but the relationship between them becomes so warped that outside observers can never see events that occur there. From the perspective of someone falling into a black hole, crossing the event horizon is unremarkable. Time flows normally, space curves smoothly, and there's no dramatic moment when the laws of physics suddenly change. The falling observer simply continues inward, following a geodesic through increasingly curved space-time until reaching the central singularity where the curvature truly does become infinite. But from the perspective of someone watching from a safe distance, the story is completely different. As the falling observer approaches the event horizon, they appear to slow down dramatically. Light from the falling observer becomes increasingly red-shifted, stretched to longer wavelengths by the intense gravitational field. Time dilation becomes more and more extreme until, at the moment the observer would cross the horizon, they appear to freeze completely. This frozen image remains visible to outside observers forever, though it fades exponentially as the light becomes red-shifted beyond detectability. From the outside perspective, nothing ever actually crosses the event horizon. Objects simply approach it asymptotically, becoming dimmer and redder until they effectively disappear. This creates a profound paradox about the very existence of black hole interiors. If nothing can ever be observed to cross the event horizon, in what sense do black holes have interiors at all? This question touches on fundamental issues about the nature of reality and whether things exist independently of our ability to observe them. The paradox becomes even more acute when we consider Stephen Hawking's discovery that black holes emit thermal radiation. In 1974, Hawking used quantum field theory in curved spacetime to show that the intense gravitational fields near black holes cause virtual particle pairs to become real. One particle from each pair falls into the black hole, while the other escapes, creating a steady stream of radiation that carries energy away from the black hole. This Hawking radiation causes black holes to slowly evaporate over time. The rate of evaporation is inversely related to the black hole's mass, so smaller black holes evaporate faster than larger ones. A black hole with the mass of our Sun would take approximately 10 to the 67 years to evaporate completely, far longer than the current age of the universe. But microscopic black holes, if they exist, would disappear in tiny fractions of a second. The discovery of Hawking radiation revealed that black holes have temperature and entropy, thermodynamic properties that seem to connect them to information theory in profound ways. Jacob Bekenstein had proposed in 1973 that black holes should have entropy proportional to their surface area rather than their volume, suggesting a deep connection between gravity and information. The temperature of a black hole is inversely proportional to its mass. Stellar mass black holes have temperatures of only a few billionths of a degree above absolute zero, making their Hawking radiation completely negligible compared to the cosmic microwave background radiation. But the theoretical implications are enormous, suggesting that black holes are not the perfectly black objects they were once thought to be. This connection between black holes and thermodynamics became clearer with the development of the holographic principle. If all the information in a volume of space can be encoded on its boundary, then the entropy of a black hole, proportional to its surface area, makes perfect sense. The information that falls into a black hole might be stored holographically on the event horizon, remaining accessible to outside observers even though they can never see it directly. But this leads to another puzzle about causality and time near black holes. If information is stored on the event horizon, and if that horizon represents the boundary between events that can communicate with the outside universe and events that cannot, then what determines which information gets stored and which gets lost? The information paradox, as it's come to be known, represents one of the deepest unsolved problems in theoretical physics. If black holes truly destroy information when they evaporate, they would violate one of the most fundamental principles of quantum mechanics. But if information is preserved, it must be encoded in the Hawking radiation in ways that seem to require faster than light communication between the interior and exterior of the black hole. Recent theoretical work has suggested various resolutions to this paradox. Some physicists propose that black holes are actually fuzzballs, complex quantum objects without true event horizons. Others suggest that the interior and exterior of a black hole are connected through wormholes that preserve information through quantum entanglement. Still others argue that information is released during the final moments of black hole evaporation through mechanisms we don't yet understand. These theoretical investigations have led to new insights about the relationship between space-time geometry and quantum information. Some researchers now believe that space-time itself emerges from patterns of quantum entanglement, with black holes serving as laboratories, where this deep connection becomes most apparent. Inside a black hole, the situation becomes even stranger. All time-like paths, all possible futures for any object inside the horizon, lead inevitably toward the central singularity. In a sense, the singularity represents the unavoidable future for everything inside the black hole. Time becomes space-like, and what we normally think of as spatial directions becomes time-like. This reversal of the roles of space and time inside black holes creates a situation where the future becomes as inevitable as falling downward in Earth's gravity. Just as you cannot choose to fall upward when you step off a cliff, objects inside black holes cannot choose to avoid the singularity. All paths through space-time lead there with mathematical certainty. This raises profound questions about free will and determinism in the most extreme gravitational environments. If the future is completely determined for anything inside a black hole, does this represent the ultimate expression of gravitational determinism? Or does it reveal fundamental limitations in our classical understanding of space-time that must be resolved by quantum gravity? Recent computer simulations of black hole interiors have revealed complex dynamics that suggest something like anticipatory behavior. The space-time geometry inside a black hole evolves in ways that seem to prepare for the formation of the central singularity, even when that singularity is still far in the future from the perspective of infalling matter. These simulations show that the curvature patterns inside black holes naturally organize themselves into configurations that channel all matter and energy toward the center. The geometry itself seems to know where everything is headed and shapes itself to guide matter along the appropriate paths toward the inevitable singularity. This apparent guidance might reflect the same kind of geometric encoding of future motion that we discussed for orbital systems, but taken to an extreme where all possible futures converge on a single outcome. The gravitational field inside a black hole might represent the ultimate example of geometric determinism, where the curvature of space-time completely determines the fate of everything within it. The story becomes even stranger when we consider what happens when black holes merge. When two black holes spiral toward each other, their event horizons eventually merge, creating a single, larger black hole. During this process, the space-time geometry becomes extremely dynamic, with gravitational waves carrying away energy and angular momentum. Computer simulations of these mergers reveal that the final black hole settles into a simple, symmetric configuration described by just 3 parameters: mass, electric charge, and angular momentum. All other information about the original black holes, their internal structure, their formation history, everything that made them unique, seems to disappear completely into what physicists call the no-hair theorem. This loss of information during black hole mergers creates another puzzle about causality and time in strongly curved space-time. If information is truly lost, then the evolution of space-time becomes irreversible in a fundamental way. The future state of the system cannot be used to reconstruct its past, violating time reversal symmetry that characterizes most physical laws. The merger process itself reveals fascinating aspects of how extreme gravity shapes the flow of time. In the final moments before two black holes combine, they orbit each other at significant fractions of the speed of light. Time dilation effects become extreme, and the geometry of space-time becomes so dynamic that even the concept of simultaneity breaks down completely. From the perspective of matter falling into one of the merging black holes, the merger might appear to take place over a reasonable period of time. But from the perspective of a distant observer, the entire merger process appears to be frozen at the moment the event horizons touch, with the subsequent evolution redshifted beyond detectability. This creates a strange situation where the most violent events in the universe, black hole mergers that generate gravitational waves powerful enough to shake space and time across billions of light years, appear to never quite finish from the perspective of outside observers. The final moments of the merger are forever frozen at the boundary between what can be observed and what remains hidden behind the event horizon. Some physicists have speculated that this freezing of time at event horizons might be related to the apparent anticipatory behavior we've discussed throughout our investigation. If information about the future evolution of gravitational systems is encoded in the present structure of space-time, then the event horizon might represent a boundary where this encoding becomes perfect and complete. Inside the black hole, all information about the future evolution of the system toward the singularity would be encoded in the present geometry. Outside the black hole, information about the past history of everything that has fallen in would be encoded holographically on the event horizon. The horizon itself might represent a kind of interface between past and future, where gravitational information is processed and preserved, but these ideas remain highly speculative, far from experimental verification. What we know for certain is that black holes represent the most extreme laboratories for studying gravity's relationship with time and causality. They reveal that, in the strongest gravitational fields, the normal relationship between cause and effect can break down in ways that challenge our most basic assumptions about the nature of reality. The apparent freezing of time at event horizons, the unavoidable futures inside black holes, the loss of information during mergers, and the possible connections between distant black holes through quantum entanglement all suggest that gravity operates according to rules that we're only beginning to understand. As we've seen throughout this exploration, the question of whether gravity knows the future becomes increasingly complex the deeper we probe. Black holes represent the extreme endpoint of this complexity, where the very concepts of past, present, and future might need to be fundamentally reconsidered. The event horizon acts as a one-way membrane in space-time, allowing information to flow inward, but never outward. This creates a fundamental asymmetry in the flow of information that might be key to understanding gravity's apparent relationship with time. Information about the past can be encoded on the horizon and preserved forever, while information about the future evolution inside the black hole remains hidden from outside observers. This asymmetry might explain why gravity seems to anticipate future motion in stable orbital systems, while still respecting causality. The gravitational field can encode information about past motion and current momentum in ways that naturally predict future evolution, but it cannot access information that truly originates in the future. Black holes thus serve as cosmic laboratories where the deepest questions about gravity, time, and information converge. They trap not just matter and energy, but perhaps the very concepts of past and future, forcing us to reconsider our most basic assumptions about the nature of time itself. Some have asked, if black holes trap the past, is there any way gravity could reach toward the future? The answer might depend not on exotic properties of black holes themselves, but on how gravitational influences propagate through space-time, and whether they truly respect the cosmic speed limit that governs all other physical phenomena. On September 14, 2015, at 9:51 Coordinated Universal Time, humanity heard the universe sing for the first time. Two black holes, each about 30 times the mass of our Sun, completed a death spiral that had been going on for billions of years. In the final moments before collision, they whipped around each other at significant fractions of the speed of light, generating gravitational waves so powerful that they briefly outshone all the stars in the observable universe in gravitational radiation. These waves propagated outward through space at the speed of light, carrying with them information about one of the most violent events in cosmic history. When they reached Earth, they passed through our planet as easily as light passes through glass, stretching and compressing space itself by amounts smaller than 1/10,000th the width of a proton. But human ingenuity had prepared for this moment. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected these infinitesimal changes and opened an entirely new window on the universe. This detection represented far more than just another astronomical discovery. It provided the first direct evidence that gravitational waves exist, confirming one of Einstein's most subtle predictions a full century after he first proposed it. More importantly for our investigation, It offered a way to test whether gravity truly respects the speed of light limit that governs all other known phenomena in physics. Einstein's original prediction of gravitational waves emerged naturally from the field equations of general relativity. Just as accelerating electric charges produce electromagnetic waves that propagate at the speed of light, accelerating masses should produce gravitational waves that ripple outward through the fabric of space-time itself. These waves would carry energy away from their sources, causing orbiting systems to gradually lose energy and spiral inward. But Einstein was deeply ambivalent about his own prediction. The waves seemed impossibly weak, and he wasn't entirely convinced they were real rather than mathematical artifacts of his coordinate system. In 1936, he even submitted a paper arguing that gravitational waves didn't exist, though he withdrew it after colleagues pointed out errors in his calculation. The reality of gravitational waves was finally established through theoretical work in the 1950s and 60s and indirect observational evidence in the 1970s. The Hulse-Taylor pulsar, which we discussed earlier, provided compelling evidence that binary systems really do lose energy through gravitational wave emission at exactly the rate Einstein's theory predicted. But direct detection remained elusive for decades. The fundamental challenge is that gravitational waves interact incredibly weakly with matter. Unlike electromagnetic waves, which can be absorbed and reflected by charged particles, gravitational waves pass through ordinary matter almost as if it weren't there. This makes them extraordinarily difficult to detect, but it also means they carry pristine information about their sources across cosmic distances. The LIGO detectors overcome this challenge through exquisite precision and clever design. Each detector consists of two perpendicular arms, each 4 kilometers long, with laser light bouncing back and forth between mirrors at the ends. When a gravitational wave passes through the detector, it alternately stretches one arm while compressing the other, creating tiny changes in the light travel time that can be measured using laser interferometry. The sensitivity required is mind-boggling. LIGO can detect changes in the arm lengths that are 10,000 times smaller than the width of a proton. This is equivalent to measuring the distance to the nearest star to an accuracy smaller than the width of a human hair. Achieving this sensitivity required decades of technological development and the solution of countless engineering challenges. But the payoff has been extraordinary. Since that first detection in 2015, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Most come from merging black holes, but the detectors have also observed neutron-star collisions and may eventually detect waves from more exotic sources like cosmic strings or the primordial gravitational waves generated during cosmic inflation. Each detection provides new insights into the nature of gravity and its relationship with space and time. But perhaps the most important discovery for our investigation came on August 17, 2017, when LIGO and Virgo detected gravitational waves from two merging neutron stars. This event, catalogued as GW 170817, provided the first opportunity to test whether gravitational waves truly travel at the speed of light or whether they might move faster or slower. The key came from the fact that neutron star mergers don't just produce gravitational waves, they also create spectacular displays of electromagnetic radiation. The collision of two neutron stars generates gamma-ray bursts, optical transients, and radio emissions that can be detected by conventional telescopes. If gravitational waves and electromagnetic waves travel at different speeds, they should arrive at Earth at different times from the same distant source. The results were unambiguous. The gravitational waves from GW 170817 arrived at Earth just 1.7 seconds before the gamma-ray burst from the same event. Given that the source was about 130 million light-years away, this tiny time difference could easily be explained by the different mechanisms that generate gravitational waves and gamma rays during the merger process. More importantly, the near-simultaneous arrival of gravitational and electromagnetic signals placed extraordinarily tight constraints on any difference between their propagation speeds. The measurements showed that gravitational waves travel at the speed of light to an accuracy of better than 1 part in 10 to the 15th power. This is one of the most precise tests of relativity ever performed. This result has profound implications for our understanding of gravity's relationship with causality. It confirms that gravitational influences, like all other causal influences in physics, are limited by the speed of light. There is no evidence that gravity can transmit information faster than light, no indication that it operates outside the normal constraints of relativistic causality. But this raises a puzzle we've been grappling with throughout our investigation. If gravitational waves travel at exactly the speed of light, and if changes in gravitational fields propagate no faster than these waves, how can orbital systems maintain their stability over cosmic timescales? How can binary stars remain bound for billions of years if each star is responding to where the other was when gravitational waves left its surface? The answer, as we've discussed, lies in the sophisticated mathematical structure of Einstein's field equations. The waves that LIGO detects carry information about accelerations, not positions or velocities. They represent ripples in space-time caused by rapid changes in the distribution of mass and energy. But the quasi-static gravitational fields that determine orbital motion evolve much more smoothly, without generating significant wave radiation. This distinction is crucial for understanding how gravity can appear to act instantaneously while still respecting the speed of light limit. The background curvature of space-time, which determines the geodesic paths that objects follow, can remain approximately synchronized across a gravitational system even though changes propagate at finite speed. Only rapid accelerations generate waves that carry energy away from the system. It's analogous to the difference between ocean waves and ocean currents. Waves propagate across the water surface at a specific speed, carrying energy and information about distant storms. But the underlying currents can create coherent flow patterns across vast regions without generating significant wave activity. Similarly, gravitational waves propagate through space-time at light speed, but the underlying geometry can maintain coherent patterns that guide orbital motion without violating causality. The LIGO detections have also revealed new insights into the nature of space-time itself. Each gravitational wave event provides a direct measurement of space-time curvature, allowing scientists to test Einstein's predictions under conditions that were impossible to access before. The results have consistently confirmed general relativity with remarkable precision. But perhaps most intriguingly, gravitational wave astronomy has begun to reveal phenomena that were previously invisible to electromagnetic observations. Black hole mergers, neutron-star collisions, and other extreme gravitational events create signatures in space-time curvature that have no electromagnetic counterpart. We're literally hearing the universe in a new way, accessing information that no other type of astronomy can provide. Future gravitational wave detectors will push these capabilities even further. The Laser Interferometer Space Antenna, LISA, will operate in space with arm lengths of millions of kilometers, making it sensitive to gravitational waves from supermassive black hole mergers and other low-frequency sources. Ground-based detectors like the proposed Einstein telescope will achieve even greater sensitivity, potentially detecting gravitational waves from neutron star formations, or even exotic phenomena like cosmic strings. These future observations may reveal whether there are any circumstances under which gravity's relationship with the speed of light becomes more complex. Some theoretical models predict tiny deviations from general relativity that could show up in gravitational wave observations from extreme sources. Others suggest that quantum gravitational effects might create subtle modifications to wave propagation over cosmic distances. But so far, Every observation has confirmed that gravitational waves travel at exactly the speed of light, with no evidence for faster-than-light propagation or other exotic behavior. This consistency across dozens of detections and a wide variety of source types provides strong evidence that gravity truly does respect the relativistic speed limit. The precision of these measurements also places severe constraints on alternative theories of gravity. Many proposed modifications to general relativity predict that gravitational waves should travel at speeds different from light, or that different polarizations of gravitational waves should propagate at different speeds. The LIGO observations have ruled out most of these alternatives with extraordinary precision. This doesn't mean that our understanding of gravity is complete. The merger events that LIGO observes probe gravity in regimes of extreme curvature and high energy density that we can't replicate in Earth-based laboratories. Each detection provides new data about how space-time behaves under conditions that push our theoretical understanding to its limits. Some of the most intriguing observations involve the final moments of black hole mergers, where the curvature of space-time becomes so extreme that nonlinear effects dominate the evolution. These events provide direct tests of Einstein's field equations in their full, nonlinear glory, confirming that our mathematical understanding of space-time geometry remains accurate even under the most extreme conditions. The ring-down phase that follows each merger is particularly revealing. After two black holes combine, the resulting object settles into its final state by emitting gravitational waves with characteristic frequencies and decay times. These ring-down waves provide a direct measurement of the fundamental properties of black holes, confirming theoretical predictions about their mass, spin, and structure. Perhaps most remarkably, these observations show that black holes really do behave like the simple objects that general relativity predicts. Despite their exotic properties and the extreme physics involved in their formation, black holes settle into configurations described by just three parameters: mass, electric charge, and angular momentum. All other information about their history is erased, exactly as Einstein's theory predicts. This erasure of information during black hole formation and merger raises deep questions about the relationship between gravity, quantum mechanics, and the nature of information itself. But it also demonstrates the extraordinary predictive power of general relativity, even in regimes far beyond those that Einstein could have imagined when he first formulated the theory. The gravitational wave observations have also begun to reveal patterns in the population of black holes throughout the universe. The masses and spins of merging black holes provide clues about how these objects form and evolve over cosmic time. Some mergers involve black holes with properties that are difficult to explain using conventional formation scenarios, suggesting that our understanding of stellar evolution and black hole physics may need refinement. Future detections may reveal even more exotic phenomena. Some theoretical models predict the existence of primordial black holes formed in the early universe, or black holes with unusual properties that could provide evidence for physics beyond the standard model. Gravitational wave astronomy offers a unique way to search for such objects, since they would create distinctive signatures in space-time curvature. But for our central question about gravity's relationship with time and causality, the message from gravitational wave astronomy is clear. Gravity respects the speed of light limit with extraordinary precision. There is no evidence that gravitational influences propagate faster than light. No indication that gravity operates outside the normal constraints of relativistic causality. This doesn't resolve all the puzzles we've discussed about gravity's apparent anticipatory behavior. The sophisticated error correction mechanisms built into Einstein's field equations still allow gravitational systems to maintain remarkable stability despite the finite speed of wave propagation. The geometric encoding of momentum and acceleration information in space-time curvature still creates what appears to be prescient behavior in complex gravitational systems. But it does establish that any such behavior must operate within the fundamental constraints of relativity. Gravity cannot cheat causality by transmitting information faster than light. Whatever mechanisms allow it to maintain orbital stability and create apparent anticipation must work through the standard channels of relativistic physics. If gravity doesn't beat light, why does it sometimes feel more fundamental, like it's baked into time itself? The answer may lie not in any special relationship between gravity and the future, but in the deep philosophical questions about the nature of time itself and gravity's role in shaping the stage on which all physical events unfold. Albert Einstein once wrote to his lifelong friend Michel Besso, shortly after Besso's death, that for us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. This wasn't merely poetic consolation from a grieving friend. It was a profound statement about the nature of time itself, emerging from decades of wrestling with the implications of relativity and the geometric view of space-time. Einstein's words capture one of the most unsettling aspects of modern physics. Our everyday experience tells us that time flows like a river, carrying us inexorably from past through present toward future. We remember yesterday, experience today, and anticipate tomorrow. The future seems open and undetermined, full of possibilities that our choices and actions will help shape. But Einstein's equations paint a very different picture of temporal reality. In the four-dimensional space-time of general relativity, past, present, and future coexist as different regions of a single, unchanging mathematical structure. What we experience as the passage of time is really just the unfolding of our consciousness through this static four-dimensional block. The future isn't approaching us, we're approaching the future, following our world lines through a space-time that contains all of history simultaneously. This block universe view, also known as eternalism, has profound implications for our understanding of gravity's apparent relationship with time. If the future already exists as part of the four-dimensional structure of space-time, then gravity's apparent ability to anticipate future motion becomes less mysterious. The curvature at any point in space-time naturally reflects the distribution of matter and energy throughout the entire four-dimensional block, including regions we consider to be in the future. From this perspective, an object following a geodesic through curved space-time isn't really anticipating future events. It's simply following a path that was always there in the four-dimensional geometry. The appearance of anticipation emerges from our three-dimensional, time-based perspective on what is fundamentally a four-dimensional, geometric reality. Consider the analogy of a mountain road that winds up a steep slope. From the perspective of a driver navigating the curves, each turn seems to anticipate the terrain ahead, following a path that responds to geographic features that haven't yet come into view. But from an airplane overhead, the entire road is visible simultaneously. The road doesn't anticipate the mountain. It simply follows the most efficient path through a landscape that exists all at once. Similarly, gravitational geodesics don't anticipate future mass distributions. They follow the most efficient paths through a four-dimensional space-time landscape that includes all of time simultaneously. What appears to be gravitational foresight is really just the geometric expression of this eternal, four-dimensional reality. But this block universe view raises deeply troubling questions about the nature of human experience and free will. If the future already exists with the same ontological status as the past, what meaning can we attach to choice, change, or moral responsibility? Are we simply playing out a cosmic script that was written in the geometry of space-time from the beginning of time? Some philosophers and physicists have embraced this deterministic vision, arguing that free will is indeed an illusion, and that our sense of agency is just a byproduct of our limited perspective on the four-dimensional whole. Others have sought to preserve human agency by arguing that the block universe is compatible with meaningful choice, even if the outcomes of our choices are already encoded in the structure of space-time. The debate becomes even more complex when we consider the role of quantum mechanics. While general relativity suggests a deterministic block universe where the future is as fixed as the past, quantum mechanics introduces fundamental randomness that seems to make the future genuinely open and undetermined. The collapse of quantum wave functions appears to create genuine novelty, bringing new information into existence that wasn't previously encoded in the state of the universe. This tension between the deterministic geometry of general relativity and the probabilistic evolution of quantum mechanics lies at the heart of the measurement problem in quantum mechanics. When and why does a quantum system transition from a superposition of possibilities to a definite outcome? And what role does gravity play in this transition? Some physicists have proposed that gravity itself might be responsible for quantum wave function collapse. In this view, the curvature of space-time created by massive objects causes quantum superpositions to decohere, forcing quantum systems to adopt definite classical properties. If this is true, then gravity's relationship with time becomes even more fundamental, serving as the mechanism that transforms quantum possibilities into classical realities. Roger Penrose has suggested that quantum gravity effects in the brain might be responsible for consciousness itself. In his theory, microscopic quantum processes in neural microtubules remain in superposition until gravitational effects cause them to collapse, creating moments of conscious awareness. While this theory remains highly controversial, it illustrates how gravity's relationship with time might extend even to the nature of subjective experience. But even without exotic theories of quantum consciousness, the philosophical implications of gravity's temporal relationships are profound. The geometric view of space-time suggests that what we call causation might be better understood as geometric correlation. Events don't cause other events to happen, they're simply connected through the four-dimensional structure of space-time in ways that create the appearance of causal relationships from our time-based perspective. This geometric view of causation has led some physicists to propose that the laws of physics themselves might be emergent properties of space-time geometry, rather than fundamental rules that govern how matter behaves. In this view, conservation of energy and momentum aren't separate physical laws, but automatic consequences of the geometric symmetries of space-time. Gravity doesn't obey conservation laws, it embodies them in its very structure. The implications extend beyond physics into questions about the nature of existence itself. If space-time is fundamental and matter is derivative, as general relativity suggests, then physical objects might be better understood as patterns in the geometry of space-time, rather than things that exist within space-time. A planet isn't a separate object moving through curved space-time. It's a particular configuration of space-time curvature that we interpret as a solid, moving object. This view, sometimes called relationalism, suggests that space and time don't exist independently of the objects and events they contain. Instead, spatial and temporal relationships emerge from the patterns of interaction between physical systems. There is no absolute space or time, only the web of relationships between events that creates the structure we experience as space-time. From a relationalist perspective, gravity's apparent anticipation of future motion becomes even less mysterious. There are no separate objects pulling on each other across space and time. There are only patterns of relationship that extend throughout the four-dimensional structure of space-time, creating correlations between events that we interpret as gravitational influences. But relationalism raises its own puzzles about the nature of time and existence. If space and time emerge from relationships between events, what determines which relationships are possible and which are not? Why does space-time have the particular geometric structure described by Einstein's field equations, rather than some other structure? Some physicists have suggested that the structure of space-time itself might be determined by information-theoretic principles. In this view, the geometry of space-time emerges from the processing and storage of quantum information in ways that optimize the flow of information through the universe, gravity becomes not just a geometric phenomenon, but an information processing phenomenon, with black holes serving as cosmic computers that manipulate quantum information on scales we can barely imagine. This information theoretic view of gravity has led to new insights about the nature of time itself. Some researchers propose that time is fundamentally about the processing of information, rather than the flow of some absolute temporal substance. The arrow of time, our experience of moving from past to future, might emerge from the tendency of information to become more scattered and complex over time, creating the thermodynamic arrow that distinguishes past from future. In this view, gravity's relationship with time becomes even more intimate. The curvature of space-time doesn't just determine how objects move through time, it determines how information flows and processes throughout the universe. The apparent anticipatory behavior of gravitational systems might reflect the optimal information processing capabilities of space-time geometry itself. But these information theoretic approaches raise new questions about the relationship between physical reality and mathematical description. If space-time emerges from information processing, what determines the rules of that processing? Are we simply pushing the mystery back one level, replacing questions about the nature of space-time with questions about the nature of information? The philosophical implications become even more complex when we consider the possibility that our universe might be one of many, part of a vast multiverse where different regions of space have different physical laws and different geometric structures. In this view, the particular properties of space-time in our observable universe, including its apparent anticipatory gravitational behavior, might be just one possibility among countless others. Some versions of multiverse theory suggest that all mathematically possible universes exist with equal reality, including universes where gravity does violate causality, where faster-than-light communication is possible, or where time flows backward. Our universe would be special only in that it happens to have physical laws compatible with the existence of observers like ourselves. This anthropic reasoning provides one possible explanation for why gravity appears to have just the right properties to create stable planetary systems and long-lived stars. In universes where gravity behaved differently, perhaps being too weak to hold planets in orbit, or too strong to allow star formation, there would be no observers to contemplate the nature of gravitational interactions. But anthropic explanations are philosophically unsatisfying to many physicists, who prefer to seek deeper principles that might explain why the laws of physics have their observed forms. The search for such principles has led to investigations of mathematical structures that might underlie physical reality, including explorations of whether the universe itself might be a mathematical object, rather than something described by mathematics. In this mathematical universe hypothesis, physical reality and mathematical reality are identical. The reason that mathematics describes the universe so perfectly isn't because we've discovered mathematical laws that govern physical phenomena, but because physical phenomena are mathematical phenomena. Space, time, matter, and energy are all aspects of an underlying mathematical structure that we experience from the inside. From this perspective, gravity's relationship with time becomes a question about the mathematical structure of space-time geometry rather than a question about physical causation. The apparent anticipatory behavior of gravitational systems reflects the mathematical relationships encoded in the geometry of four-dimensional space-time, relationships that exist timelessly in the abstract mathematical realm. But even this mathematical view raises questions about why we experience time as flowing if it's really just another dimension in a static mathematical structure. Why do we remember the past but not the future? Why does entropy increase over time? Why do we experience ourselves as moving through time rather than existing timelessly at all moments simultaneously? These questions touch on some of the deepest mysteries in physics and philosophy. They connect our investigation of gravity's relationship with time to fundamental questions about consciousness, free will, the nature of existence, and our place in the cosmic order. The answers we give to these questions shape not just our understanding of gravity, but our understanding of what it means to be human in a universe governed by mathematical laws. The geometric view of gravity suggests that time is more fundamental than we might have imagined. Rather than being a backdrop against which physical events unfold, time appears to be woven into the very fabric of physical reality. The curvature of space-time doesn't evolve in time. It includes time as an integral part of its structure. Gravity doesn't act through time, it acts on time itself, shaping the flow of temporal experience throughout the universe. This intimate relationship between gravity and time has led some physicists to speculate that time itself might be an emergent property of gravitational interactions. In this view, our experience of temporal flow emerges from the way that gravitational fields process and correlate information across space. Without gravity to create correlations between distant events, there might be no coherent notion of simultaneity or temporal sequence. The possibility that time emerges from gravity rather than gravity operating within a pre-existing temporal framework represents a complete reversal of our normal way of thinking about physical causation. Instead of asking how gravitational influences propagate through time, we might need to ask how time emerges from the pattern of gravitational correlations throughout the universe. But whether time is fundamental or emergent, whether the block universe is real or just a mathematical convenience, whether gravity anticipates the future or simply embodies it, one thing seems clear. The relationship between gravity and time is far more intimate and mysterious than Newton or even Einstein might have imagined. Gravity doesn't just bend space, it bends our understanding of temporal reality itself. This brings us back to our original question, but with a new perspective. Instead of asking whether gravity knows the future, we might ask whether the distinction between knowing and being, between anticipation and embodiment, makes sense when applied to the fundamental structure of space-time itself. Does gravity know the future, or does gravity help create what we call the future through its role in shaping the geometric structure of reality? Which brings us to what gravity actually tells us about the now and the not yet. Throughout our journey into the relationship between gravity and time, we've encountered a persistent intuition that gravity somehow knows where objects are going before they get there. This intuition is so compelling that it has led to decades of speculation about whether gravity might operate outside the normal rules of causality, transmitting information faster than light, or even reaching into the future to guide present motion. But as we've seen, this intuition, while understandable, is based on a fundamental misunderstanding of how gravity actually works. The apparent foresight of gravitational interactions doesn't reflect any violation of causality or any special relationship with future events. Instead, it emerges from the sophisticated mathematical structure of Einstein's general relativity and the geometric nature of space-time itself. To understand why the misconception persists, we need to examine how our everyday experience of gravity differs from the reality described by modern physics. When you drop a ball, it falls in a smooth parabolic arc that seems to know exactly where it's going from the moment it leaves your hand. The trajectory appears predetermined, as if gravity has already calculated the entire future path and is guiding the ball along it. This appearance of predetermination is reinforced by our ability to predict the ball's motion with extraordinary precision using the equations of physics. Given the initial position and velocity, we can calculate exactly where the ball will land, when it will get there, and what path it will follow. This predictive power makes it seem as if the future motion is somehow encoded in the present gravitational field. But this reasoning confuses mathematical predictability with physical predetermination. The fact that we can predict the ball's motion doesn't mean that the gravitational field contains information about future events. It means that the mathematical laws of physics, when applied to present conditions, allow us to calculate how those conditions will evolve over time. The predictive power of physics comes from the deterministic nature of the underlying equations, not from any mysterious ability of physical fields to access future information. Newton's laws, Einstein's field equations, and the other mathematical frameworks we use to describe gravity are deterministic systems where the present state completely determines the future evolution. But this mathematical determinism doesn't require any faster than light communication or temporal pressions. Consider an analogy with a simple mechanical system like a pendulum. Once we know the pendulum's current position and velocity, we can predict its entire future motion with perfect accuracy. The pendulum will swing back and forth in a predictable pattern that we can calculate arbitrarily far into the future. But this doesn't mean that the pendulum knows where it's going, or that mysterious forces are guiding it along predetermined paths. The pendulum simply follows the laws of physics, which happen to be deterministic for this type of system. The future motion emerges naturally from the present state according to mathematical rules, not because the future already exists somewhere waiting to be accessed. The same principle applies to gravitational systems, even though the mathematics is much more complex. The misconception about gravitational foresight is also reinforced by the way we typically describe orbital motion. We say that Earth orbits the Sun because the Sun's gravity pulls it along an elliptical path. This language makes it sound as if gravity reaches out across space to grab Earth and drag it around the Sun, requiring some kind of communication between the two objects. But as we've learned, gravity doesn't pull objects through space at all. Instead, massive objects like the Sun create curvature in the fabric of space-time itself, and other objects like Earth simply follow the straightest possible paths through that curved geometry. There's no pulling, no communication, and no need for the Sun to know where Earth is or where it's going. Earth's orbital motion is simply the natural consequence of following a geodesic through the curved space-time created by the Sun's mass. The curvature encodes information about the Sun's mass, position, and motion, but it doesn't encode information about future events. The apparent stability and predictability of the orbit emerge from the geometric properties of space-time, not from any prescient guidance system. The confusion is compounded by the way gravitational interactions are often portrayed in popular science. Animations and diagrams frequently show gravitational fields as arrows or lines of force, reaching out from massive objects to pull on other objects. While these visualizations can be helpful for understanding the effects of gravity, they reinforce the misleading notion that gravity involves direct action at a distance. In reality, gravitational effects are completely local. The curvature of space-time at any point depends only on the matter and energy in the immediate vicinity of that point. Objects respond only to the local curvature of space-time, where they happen to be located. There's no reaching across space, no communication between distant objects, and no need for non-local coordination. This local nature of gravitational interactions resolves many of the apparent paradoxes about gravitational foresight. When we observe that binary star systems remain stable despite the finite speed of light, we don't need to invoke faster than light communication or temporal prescience. The stability emerges from the local geometric properties of curved space-time, properties that naturally encode information about momentum and motion in ways that maintain orbital coherence. Another common misconception involves the relationship between gravitational waves and gravitational fields. Some people assume that because gravitational waves travel at the speed of light, gravitational fields must also propagate at that speed, creating retardation effects that should destabilize orbital systems. But this confuses two different aspects of gravitational physics. Gravitational waves are ripples in space-time curvature that propagate outward from accelerating masses. These waves do indeed travel at the speed of light, and carry information about the acceleration history of their sources. But the quasi-static gravitational fields that determine orbital motion are not the same as gravitational waves. They represent the background curvature of space-time that evolves much more slowly than the wave phenomena. The distinction is similar to the difference between ocean waves and ocean currents. Waves propagate across the water surface at a specific speed, carrying energy and information about distant storms. But the underlying currents can create coherent flow patterns across vast regions without generating significant wave activity. The waves and currents are related phenomena, but they operate on different timescales and follow different propagation rules. In gravitational physics, the background curvature that determines orbital motion can remain approximately synchronized across a gravitational system, even though rapid changes propagate at light speed through gravitational waves. This is because orbital motion typically involves timescales much longer than the light crossing time of the system, allowing the quasi-static field to adjust smoothly without generating significant wave radiation. The mathematical machinery that makes this work is built into Einstein's field equations through the conservation laws and constraint equations that ensure energy and momentum are preserved throughout spacetime. These mathematical relationships automatically generate the right combination of retarded effects and compensating terms to maintain orbital stability without requiring any violation of causality. But perhaps the most persistent misconception about gravitational foresight involves the interpretation of computer simulations and theoretical calculations. When physicists model complex gravitational systems like merging black holes or colliding galaxies, they often find that the systems evolve in ways that seem to anticipate future events. Orbits adjust in advance of close encounters, merger dynamics prepare for final coalescence, and the overall evolution seems guided by knowledge of the eventual outcome. These apparent anticipatory behaviors are real features of the gravitational dynamics, but they don't reflect any mystical foresight on the part of gravity itself. Instead, they emerge from the non-linear mathematical structure of Einstein's field equations, which can generate complex, seemingly intelligent behaviors from simple, local interactions. Nonlinear systems throughout physics display similar apparent intelligence. Weather systems seem to know how to organize themselves into coherent patterns like hurricanes and jet streams. Biological systems seem to know how to coordinate complex behaviors like flocking in birds or schooling in fish. Economic markets seem to know how to process vast amounts of information and reach efficient outcomes. In each case, the apparent intelligence emerges from the collective behavior of simple components following local rules. No individual air molecule knows about the hurricane. No individual bird knows the flock's destination, and no individual trader knows the market's future direction. But the system as a whole can display behaviors that appear intelligent, adaptive, and goal-directed. The same principle applies to gravitational systems. No individual component of the gravitational field contains information about future events, but the system as a whole can evolve in ways that appear to anticipate and prepare for future outcomes. This apparent anticipation emerges from the mathematical structure of the field equations, not from any genuine temporal prescience. The misconception is also reinforced by the way we think about prediction and knowledge in human contexts. When we predict future events, we typically do so by gathering information, processing it mentally, and making informed guesses about what might happen. This cognitive process creates a strong association between prediction and knowledge, leading us to assume that anything capable of anticipating future events must have access to information about those events. But physical systems can display predictive behavior without having knowledge in any meaningful sense. A thermostat predicts room temperature and adjusts heating accordingly, but it doesn't know anything about thermal dynamics. A guided missile predicts the future position of its target and adjusts its trajectory accordingly, but it doesn't know anything about ballistics or navigation. These systems work through feedback mechanisms that allow present behavior to depend on the difference between current conditions and desired outcomes. The apparent prediction emerges from the feedback loop, not from any genuine foresight or knowledge about future events. Gravitational systems work similarly, but with feedback mechanisms built into the mathematical structure of space-time geometry rather than implemented through mechanical or electronic systems. The curvature at any point in space-time depends on the local distribution of matter and energy, but it also depends on how that distribution is changing over time. This creates natural feedback loops that allow the gravitational field to adjust its evolution in response to the changing conditions within it. These feedback mechanisms can create behaviors that appear predictive or anticipatory, but they operate through entirely local causal processes. The gravitational field doesn't reach into the future to gather information about upcoming events. Instead, it processes information about present conditions, including information about how those conditions are changing in ways that naturally lead to future compatible evolution. Understanding these misconceptions is crucial for developing a clear picture of how gravity actually relates to time and causality. Gravity doesn't violate the speed of light limit, doesn't communicate faster than light, doesn't access information from the future, and doesn't operate outside the normal constraints of relativistic physics. What gravity does do is demonstrate the extraordinary sophistication and elegance of Einstein's geometric approach to space-time. The apparent anticipatory behavior that we observe in gravitational systems emerges naturally from the mathematical structure of general relativity, without requiring any exotic physics or mysterious violations of causality. The field equations automatically generate exactly the right combination of effects to maintain stable orbits, create coherent large-scale structure, and produce the intricate cosmic choreography we observe throughout the universe. This isn't because gravity has special temporal powers, but because Einstein's theory provides a complete, self-consistent description of how matter and geometry interact in four-dimensional spacetime. The elegance of this mathematical structure is perhaps the most remarkable aspect of our investigation. The same equations that describe falling apples also describe orbiting planets, colliding galaxies, expanding cosmos, and merging black holes. The apparent complexity and intelligence of gravitational behavior throughout the universe emerges from a surprisingly simple geometric principle. Matter tells space-time how to curve, and curved space-time tells matter how to move. This geometric view resolves the apparent paradoxes about gravitational foresight, while preserving everything that makes gravity seem special and fundamental. Gravity doesn't need to know the future, because it helps create the future through its role in shaping the geometric structure of space-time itself. The future doesn't pre-exist waiting to be accessed. It emerges from the present through the natural evolution of curved geometry, according to Einstein's field equations. Which brings us to our final investigation of what gravity really tells us about the relationship between the present moment and the vast tapestry of events we call the future. Standing on a beach watching the tide roll in, you witness one of the most ancient and predictable phenomena on Earth. Twice each day, the ocean rises and falls in a rhythm that has persisted for billions of years. This cosmic breathing of the seas reflects the gravitational dance between Earth, Moon, and Sun, a celestial choreography so precise that we can predict high and low tides centuries into the future with remarkable accuracy. But what does this predictability really tell us about the nature of time and gravity's relationship to it? The tides don't reveal that gravity knows the future, but they do reveal something equally profound about how the present moment connects to the vast web of cosmic relationships that extend throughout space and time. Every drop of water responding to the moon's gravitational pull is following a geodesic through curved space-time. the Moon's mass warps the geometry of space and time in Earth's vicinity, creating curvature patterns that guide not just the motion of ocean water, but the motion of everything else in the region. From falling leaves to orbiting satellites, from the International Space Station to the tiniest dust particles in the upper atmosphere, everything moves along paths determined by this gravitational geometry. This geometric view reveals gravity's true relationship with time. Gravity doesn't operate in time like other forces, acting at specific moments to cause specific effects. Instead, gravity is woven into the very fabric of space-time, creating the four-dimensional stage on which all physical events unfold. Time itself becomes part of the gravitational phenomenon, rather than an external parameter within which gravity operates. To understand what this means, consider how we normally think about cause and effect. We imagine causes happening at one moment in time, followed by effects happening at later moments. A baseball pitcher throws a ball at time 1, the ball travels through the air, and the catcher catches it at time 2. This sequence creates a clear temporal ordering where cause precedes effect. But gravitational interactions don't fit neatly into this temporal framework. The curvature of space-time that guides the baseball's motion exists throughout the entire trajectory, not just at the moment of throwing or catching. The gravitational field doesn't cause the ball to follow a parabolic path in the way that the pitcher's arm causes the ball to start moving. Instead, the curved geometry of space-time makes the parabolic path the natural geodesic motion for any object moving through that region. This distinction has profound implications for our understanding of temporal relationships in physics. Traditional cause and effect relationships unfold through time, with information propagating from causes to effects at speeds no greater than light. But geometric relationships exist throughout space-time simultaneously, creating correlations between events that may be separated by vast distances and time intervals. These geometric correlations don't violate causality because they don't involve the propagation of information from one event to another. Instead, they reflect the overall structure of space-time, which includes past, present, and future as different aspects of a single four-dimensional whole. An object following a geodesic through this four-dimensional structure automatically moves in ways that appear coordinated across space and time, not because information is being transmitted, but because the geometric structure naturally creates such coordination. This is why binary star systems can remain stable for billions of years despite the finite speed of light. The stars aren't communicating with each other about their current positions and velocities. Instead, they're both following geodesics through a four-dimensional space-time geometry that naturally maintains their orbital relationship. The geometry itself encodes the conservation laws and symmetries that keep the system stable. The implications extend far beyond orbital mechanics. The large-scale structure of the universe, with its intricate web of galaxies, clusters, and cosmic voids, reflects the same kind of geometric coordination operating on cosmological scales. The gravitational field that shapes galactic motion today was laid down billions of years ago during the early phases of cosmic evolution, yet it continues to guide the present motion of matter throughout the observable universe. This temporal reach of gravitational influence doesn't represent faster-than-light communication between past and present. Instead, it reflects the fact that the gravitational field exists throughout the four-dimensional structure of space-time, connecting different epochs through geometric relationships rather than causal signals. The field that guides today's galactic motion is the same field that guided galactic motion in the past, evolved forward through billions of years of self-consistent geometric evolution. Understanding this geometric perspective helps resolve many of the apparent paradoxes we've encountered about gravity and time. Gravity appears to anticipate future motion because the geometric structure of space-time naturally encodes information about momentum, acceleration, and the evolutionary tendencies of the matter within it. Objects following geodesics through this geometry automatically move in ways that appear anticipatory from our three-dimensional, temporally sequential perspective. But this apparent anticipation isn't prediction in any conventional sense. It's more like the way a river channel anticipates the flow of water. The channel doesn't predict where the water will go, but its shape naturally guides the water along specific paths. Similarly, the curvature of space-time doesn't predict where objects will move, but its geometry naturally guides objects along geodesic paths that create the appearance of coordinated, anticipatory behavior. This analogy helps explain why gravitational systems can display such remarkable long-term stability. A well-established river channel can guide water flow for thousands of years, maintaining its basic pattern despite fluctuations in water level, seasonal variations, and minor changes in the surrounding landscape. The channel achieves this stability not through prediction or control, but through the simple fact that its shape makes certain flow patterns natural and others unnatural. Gravitational systems work similarly. The curvature patterns created by massive objects make certain types of motion natural geodesic paths, and others highly unnatural. Stable orbital configurations correspond to geodesic paths that loop back on themselves, creating closed or nearly closed trajectories through four-dimensional spacetime. These configurations persist because they represent the natural flow patterns for matter moving through the curved geometry created by gravitational sources. But unlike river channels, which are carved by external forces and remain relatively static, the geometry of spacetime is dynamic, continuously evolving in response to the matter and energy it contains. This creates a self-organizing system where the geometry shapes matter motion, and matter motion shapes the geometry in an ongoing feedback process governed by Einstein's field equations. This self-organization can produce behaviors that appear remarkably intelligent and purposeful. Gravitational systems naturally evolve toward configurations that minimize energy while conserving momentum and angular momentum. They automatically adjust to perturbations in ways that restore stability. They organize themselves into hierarchical structures that span enormous ranges of scale, from planetary systems to galaxy clusters. But this apparent intelligence emerges from the mathematical properties of the field equations, rather than from any genuine foresight or planning. The equations automatically generate solutions that satisfy conservation laws, maintain causal consistency, and produce stable long-term evolution. The intelligence is built into the geometric structure of space-time itself, not into the individual components of gravitational systems. This perspective reveals something profound about the nature of time in our universe. Time isn't just a dimension along which physical events happen to be ordered. It's an integral part of the geometric structure that determines how those events relate to each other. The flow of time that we experience isn't separate from the gravitational phenomena we observe. It's part of the same underlying geometric reality. This intimate connection between time and gravity helps explain why time behaves differently in different gravitational environments. Strong gravitational fields don't just affect the motion of objects through space, they affect the flow of time itself. Time dilation near massive objects reflects the fact that time and gravity are aspects of the same geometric phenomenon, rather than separate, independent features of physical reality. The connection also helps explain why the universe as a whole appears to have a preferred direction of time, despite the fact that most physical laws are symmetric under time reversal. The expansion of the universe, the increase of entropy, and the apparent flow of time from past to future all reflect the evolution of gravitational systems on cosmic scales. The arrow of time emerges from the same geometric dynamics that create and maintain the large-scale structure of space-time. This cosmological perspective reveals gravity's role in creating the temporal framework within which all other physical processes operate. The Big Bang didn't just create matter and energy, it created the space-time geometry within which matter and energy could evolve over cosmic time. The gravitational field that emerged from the early universe continues to provide the geometric foundation for all subsequent physical processes. From this viewpoint, asking whether gravity knows the future becomes like asking whether a foundation knows about the building constructed on top of it. The foundation doesn't predict or control what happens in the building, but it does provide the structural framework that makes the building possible. Similarly, gravity doesn't predict or control future events, but it does provide the geometric framework within which future events can unfold. This framework includes not just the spatial relationships between objects, but also the temporal relationships that determine how events can influence each other, the light cone structure that limits causal influences, the geodesic paths that determine natural motion, and the conservation laws that constrain possible changes, all emerge from the geometric properties of curved spacetime. Understanding gravity's role as the architect of spacetime geometry, rather than just another force acting within spacetime, fundamentally changes our perspective on time and causality. Instead of viewing time as an external parameter within which gravitational interactions occur, we see time as part of the gravitational phenomenon itself, inseparably woven into the fabric of geometric reality. This geometric view also provides new insights into the relationship between determinism and predictability in gravitational systems. The field equations are deterministic in the sense that the current state of the gravitational field completely determines its future evolution. But this doesn't mean that future events are somehow already present, or that the future exists in the same sense as the past. Instead, the deterministic evolution of spacetime geometry creates correlations between events at different times, without requiring those events to coexist simultaneously. The future emerges from the present through the natural unfolding of geometric relationships, not because it already exists waiting to be revealed. Gravity provides the mechanism through which present conditions give rise to future conditions, but the future remains genuinely future until the geometric evolution brings it into being. This perspective helps resolve the tension between our experience of temporal flow and the block universe picture suggested by relativity. From our embedded perspective within spacetime, we experience the unfolding of geometric relationships as temporal flow, even though the overall geometric structure may exist as a four-dimensional whole. Time feels like flow because we're part of the geometric evolution, not external observers viewing it from outside. The tides that rise and fall on our beaches thus represent far more than simple periodic motion driven by celestial mechanics. They represent the visible manifestation of the deep geometric relationships that connect our local region of spacetime to the cosmic web of gravitational influences extending throughout the observable universe. Every tidal cycle reflects the ongoing evolution of four-dimensional geometry that began with the Big Bang and continues through the present moment into the indefinite future. This cosmic perspective on apparently mundane phenomena reveals one of the most remarkable aspects of gravitational physics. The same geometric principles that govern the largest structures in the universe also determine the smallest details of motion in our everyday environment. The curvature of spacetime that shapes galactic clusters also shapes the trajectory of a thrown ball. The conservation laws that maintain cosmic structure also ensure that your coffee cup falls when you drop it. This unity of physical description across all scales of space and time suggests that gravity offers unique insights into the fundamental nature of reality itself. Unlike other forces, which operate within the framework of space-time, gravity is the framework. It provides the geometric foundation upon which all other physical phenomena are built. From this perspective, gravity's relationship with time becomes clear. Gravity doesn't know the future because it helps create the future through its role in shaping the geometric evolution of space-time. Time doesn't flow past gravity like a river flowing past a rock. Instead, gravity and time are aspects of the same underlying reality, the dynamic geometry of four-dimensional space-time that provides the stage for all physical existence. This geometric unity suggests that our original question, whether gravity knows the future before light does, was based on a false premise. Gravity and light don't compete for temporal priority because they operate in fundamentally different ways. Light propagates through space-time, carrying information from one event to another at a finite speed. Gravity is space-time, providing the geometric structure within which light propagation becomes possible. Understanding this distinction transforms our entire perspective on the relationship between matter, space, time, and information in the physical universe. Instead of viewing these as separate components that interact in complex ways, we see them as different aspects of a single unified geometric reality. Gravity doesn't transcend the normal rules of physics. It provides the foundation upon which those rules are built. What emerges from this investigation is not a picture of gravity as a mysterious force that violates causality or reaches into the future, but a picture of gravity as the architect of the space-time stage on which the drama of physical existence unfolds. Gravity tells us that time isn't just duration, space isn't just extension, and motion isn't just change of position. Instead, time, space, and motion are all aspects of dynamic geometry, the ever-evolving curvature of four-dimensional space-time that connects every event to every other event through the web of gravitational relationships that define the structure of our universe. We began this journey with a simple question born from wonder and intuition. Watching objects fall, planets orbit, and tides ebb and flow, we noticed something that seemed almost magical about gravity's behavior. It appeared to know where things were going before they got there, guiding motion with a prescience that seemed to transcend the normal rules of cause and effect. This apparent foresight led us to ask whether gravity might operate outside the speed of light limit that governs all other phenomena in physics. Perhaps gravity could communicate faster than light, or reach into the future to gather information about upcoming events. Perhaps the universe contained hidden channels of information that allowed gravitational effects to coordinate across vast distances without being constrained by relativistic causality. Our investigation has taken us through some of the deepest and most beautiful territory in modern physics. We explored the breakdown of absolute simultaneity in Einstein's relativity, where the very concept of now becomes observer-dependent, and the distinction between past, present, and future loses its universal meaning. We discovered that gravity isn't a force pulling objects through space, but the curvature of space-time itself, the dynamic geometry that provides the stage for all physical existence. We witnessed the strange case of orbital mechanics, where binary systems maintain perfect stability for billions of years, despite the finite speed of gravitational wave propagation. We explored the sophisticated error correction mechanisms built into Einstein's field equations, mathematical structures so elegant that they automatically generate exactly the right combination of effects to maintain cosmic choreography while respecting the speed of light limit. We ventured into the quantum realm, where the smooth geometry of classical space-time gives way to a foam of uncertainty and probability, and where the very concepts of space and time might emerge from deeper layers of quantum information and entanglement. We peered into the hearts of black holes, those extreme gravitational laboratories where time dilates to infinity and all possible futures converge on inevitable singularities. We examined the propagation of gravitational waves themselves, those ripples in space-time that carry information about cosmic collisions across billions of light years, arriving at Earth with exquisite precision to confirm that gravity truly respects the relativistic speed limit. we grappled with the philosophical implications of the block universe, where past, present, and future coexist in four-dimensional space-time, challenging our most basic assumptions about the nature of temporal reality. Through all of these explorations, we've discovered that the answer to our original question is both simpler and more profound than we might have expected. Gravity doesn't cheat time. It doesn't peer into tomorrow. It doesn't violate causality or communicate faster than light. But it does something far more remarkable. Gravity weaves space and time into something richer and more interconnected than our everyday experience suggests. It creates a four-dimensional tapestry where every thread connects to every other thread through geometric relationships that transcend our normal understanding of cause and effect. In this tapestry, what appears to be gravitational prescience is really the natural expression of geometric harmony, the way that curved space-time naturally guides matter along paths that create coordinated, stable, and beautiful patterns of motion. The apparent anticipatory behavior that we observe in gravitational systems emerges not from mystical foresight, but from the mathematical elegance of Einstein's geometric approach to space-time. The field equations automatically generate solutions that maintain energy and momentum conservation, preserve causal consistency, and create the stable cosmic structures we observe throughout the universe. This isn't because the equations contain magic, but because they capture something deep and true about the geometric nature of physical reality. We've learned that the misconceptions about gravitational foresight arise from our tendency to think of gravity as just another force acting within a pre-existing framework of space and time. But gravity is more fundamental than that. It is the framework itself, the dynamic geometry that creates the very concepts of space, time, distance, duration, and causal connection that we use to understand all other physical phenomena. This perspective transforms our understanding of time itself. Time isn't just a parameter that measures the duration between events. It's an integral part of the geometric structure of space-time, inseparably woven together with the three dimensions of space into a four-dimensional whole. The flow of time that we experience isn't separate from gravitational phenomena. It's part of the same underlying geometric reality. From this viewpoint, asking whether gravity knows the future becomes like asking whether a river knows where it's flowing. The river doesn't predict its path through the landscape, but its current configuration naturally determines how it will evolve as it responds to the topography around it. Similarly, gravity doesn't predict future motion, but the current curvature of space-time naturally determines how that curvature will evolve as it responds to the matter and energy within it. The beauty of this geometric understanding is that it resolves the apparent paradoxes about gravitational behavior while preserving everything that makes gravity seem special and fundamental. Orbital systems remain stable not because gravity violates causality, but because the geometric structure of space-time naturally maintains patterns that create stability. Black holes trap light and information not because they operate outside physical law, but because they represent regions where space-time curvature becomes so extreme that the normal relationship between space and time breaks down. The tides rise and fall with clockwork precision, not because the moon's gravity reaches across space to pull the oceans, but because Earth, moon, and ocean water all follow geodesics through the curved space-time created by their mutual gravitational interaction. Every drop of water in every wave is following the straightest possible path through four-dimensional geometry, creating the complex, beautiful, and utterly predictable patterns we observe from our embedded perspective within that geometry. This geometric view also provides new insights into the nature of information and computation in the universe. If space-time itself is a dynamic, evolving geometry that processes and correlates information across cosmic scales, then perhaps the apparent intelligence we observe in gravitational systems reflects a kind of cosmic computation performed by the universe itself. The stability of planetary systems, the formation of galactic structure, and the intricate dance of celestial mechanics might all emerge from information processing capabilities built into the fundamental structure of space-time. But whether or not the universe is literally computing, the geometric perspective reveals that gravity operates according to principles of information conservation and causal consistency that automatically generate behaviors that appear intelligent and purposeful. The field equations don't just describe how matter moves through space-time. They embody principles of optimization and error correction that ensure the long-term stability and coherence of gravitational systems. Looking toward the future of gravitational physics, we can anticipate discoveries that will deepen our understanding of these geometric principles. Advanced gravitational wave detectors will probe space-time curvature in regimes where quantum effects become important, potentially revealing new aspects of the relationship between geometry and information. Observations of black hole mergers and neutron-star collisions will test our understanding of gravity under the most extreme conditions in the universe. Perhaps most intriguingly, the ongoing development of quantum theories of gravity may reveal deeper layers of reality where space-time itself emerges from more fundamental quantum processes. If gravity is ultimately a quantum phenomenon, then its apparent anticipatory behavior might reflect quantum computational processes operating at scales and energies far beyond our current experimental reach. But even as we look toward these future discoveries, the investigation we've completed provides a satisfying resolution to our original question. We set out to determine whether gravity knows the future before light does, and we've discovered that this question was based on a false premise. Gravity and light don't compete for temporal priority because they operate in fundamentally different domains of physical reality. Light propagates through space-time, carrying information from one event to another at the maximum speed allowed by the causal structure of space-time. Gravity is that causal structure, the geometric framework that determines what speeds are possible and what types of information transfer can occur. Light respects the speed limit because gravity sets the speed limit through its role in determining the metric structure of space-time. The profound lesson of our investigation is that gravity doesn't need to know the future because it helps create the future through its role in shaping the geometric evolution of space-time itself. The future doesn't pre-exist somewhere waiting to be accessed. Instead, it emerges from the present through the natural unfolding of curved geometry according to Einstein's field equations. This emergence isn't random or unpredictable. The mathematical structure of general relativity ensures that the future unfolds in ways that preserve the deep symmetries and conservation laws that characterize physical reality. Energy is conserved, momentum is conserved, angular momentum is conserved, and the causal structure of space-time remains consistent as the geometry evolves from present to future. But this mathematical determinism doesn't eliminate novelty or creativity from the universe. Each moment brings genuinely new configurations of matter and energy, new patterns of space-time curvature, and new possibilities for the continued evolution of cosmic structure. The future emerges from the present not as a predetermined script, but as an ongoing creative process where geometric necessity combines with material complexity to generate endless variety and beauty. The tides that wash our shores, the planets that dance through our skies, and the stars that shine in our night sky all participate in this cosmic creativity. They follow geodesics through curved space-time not as passive objects obeying external forces, but as active participants in the ongoing evolution of four-dimensional geometry. Each orbital cycle, each tidal rhythm, and each stellar life cycle contributes to the ever-changing pattern of space-time curvature that defines the geometric structure of our universe. In the end, we discover that gravity's relationship with time is far more intimate and beautiful than we initially imagined. Gravity doesn't know the future in the way that we know facts or information. Instead, gravity helps shape the way we get there, providing the geometric foundation that allows the future to emerge from the present in a seamless curve through four-dimensional space-time. This seamless curve connects every moment to every other moment, every place to every other place, and every event to every other event through the web of gravitational relationships that extends throughout the observable universe. We are not separate observers watching this cosmic dance from outside. We are part of the dance itself, embedded in the curved geometry of space-time, following our own geodesics through the four-dimensional landscape that gravity creates and maintains. The question of whether gravity knows the future thus becomes a question about our own place in the cosmic order. We don't stand outside space-time looking in, we exist within space-time looking around. Our very ability to ask questions, to wonder about the nature of time and causality, and to investigate the deep structure of physical reality emerges from the same geometric principles that govern the motion of planets and the propagation of light. Gravity doesn't know the future, but it may help shape the way we get there. And in that shaping, in that gentle guidance of matter along geodesic paths through curved space-time, we find not prescience or predetermination, but something far more wonderful. We find the ongoing creation of a universe rich enough to contain both the mathematical beauty of Einstein's equations and the conscious beings capable of discovering and appreciating that beauty. The cosmos doesn't need to know its own future. It creates that future moment by moment, curve by curve, through the endless dance of matter and geometry that we call gravity. And in that dance, we find not just the answer to our original question, but a deeper appreciation for the profound elegance and creativity of the universe we inhabit.